Hello and welcome to Sleepy Science. What if nothing around you is truly still? Not the stone on your desk, not the air in your lungs, not the ground beneath your feet, not even empty space itself. What if stillness is only a human illusion? A calm mask worn by a universe that never stops moving? In this journey, we'll follow motion where your eyes cannot reach. Atoms trembling inside solid matter, molecules rushing through every breath. Heat hiding as invisible movement, electrons refusing to sit still, and quantum fields flickering in the vacuum. Then we'll widen the view. Earth turning beneath you, the moon pulling oceans, continents drifting, mountains rising and eroding, air flowing, oceans carrying heat, clouds forming and vanishing, the sun vibrating like a bell, stars orbiting galactic centers, and galaxies drifting with expanding space. And finally, we'll return inward to the body itself, neurons firing at rest, the heart adjusting beat by beat, cells repairing damage, proteins folding, DNA being copied, blood cells traveling, and sleep quietly running the systems that keep you alive. So before we begin, tell me in the comments what looks perfectly still to you, but might secretly be moving? Tap like if you enjoy calm science that makes reality feel strange again. Subscribe for more deep journeys into the hidden motion of existence. And now, let's step quietly into a universe where stillness was never the truth, only the speed at which humans learn to see. Atoms vibrate in solid matter. What looks completely still in your hand is secretly trembling with a motion too small for your eyes to catch. Hold a stone, a spoon, a glass of water frozen into ice, or the wooden edge of a table, and your senses tell you a simple story. This object is solid, fixed, quiet, obedient. It does not flow like a river. It does not flutter like a flame. It does not breathe, pulse, or crawl. But deep inside that stillness, below the smooth surface your fingers trust, every atom is vibrating, not traveling freely like a gas molecule, not sliding past its neighbors like a liquid, but shaking in place, held in position by invisible electrical forces. A solid is not a dead arrangement of frozen dots. It is more like a crowded room where every person is tied to their neighbors by soft springs, unable to leave their spot, yet never perfectly at rest. Each atom has a preferred place, a tiny region where the pushes and pulls around it balance. But balance does not mean silence. The atom jitters around that position, pulled back when it moves too far, pushed away when it comes too close, endlessly adjusting like a bell that never fully stops ringing. This is why solid matter can feel rigid while still being alive with microscopic motion. The table does not collapse because its atoms are linked in a stable structure, but it is not motionless. Its firmness comes from order, not from stillness. In crystals, this order can be beautifully regular, with atoms arranged in repeating patterns that stretch through the material like a hidden architecture. In glass, metal, stone, plastic, and bone, the arrangement may be more complex, more irregular, more tangled, but the same truth remains. The atoms are not sitting like statues. They are vibrating inside the boundaries created by their neighbors. You can think of the solid world as a quiet choir of tiny oscillations, where each atom hums with its own motion, and that motion can pass from one atom to the next. When sound moves through a solid, for example, it is not some ghostly substance slipping through matter. It is a coordinated disturbance, a wave of compression and relaxation traveling through these atomic connections. One region is nudged, then the next, and the vibration carries information forward. That is why sound often travels faster through solids than through air. The atoms are packed close together, tightly linked, ready to pass the disturbance along. Even the way a metal spoon rings when struck is a large-scale echo of this atomic behavior. The sound you hear begins as matter being disturbed, atoms shifting from their comfortable positions and then being pulled back again. And when a solid warms, its atoms usually vibrate with greater intensity. They move a little more widely around their positions, and in many materials this makes the object expand slightly, not because the atoms themselves become larger, but because the average spacing between them changes as their motion grows stronger. A bridge in summer, a railroad track under sunlight, a metal lid loosened by warm water. These ordinary things are quiet evidence that solid matter is not fixed in the simple way it appears. The object you call solid is always negotiating its shape through countless small motions. Scientists know this not by imagination, but through measurements. The way solids conduct heat, the way they scatter X-rays or neutrons, the way their heat capacity changes, the way sound moves through them, and the way crystals respond when disturbed. These observations all point toward the same hidden truth. The interior of a solid is dynamic. It has rhythm, it has structure, it has motion so fast and small that your body translates it as stillness. And this is where the thought becomes strangely personal. Your senses evolved for the scale of footsteps, falling branches, warm skin, moving animals, visible danger. They did not evolve to show you the tremble of atoms inside a quiet wall. So the world gives you a simplified version, a calm surface, a readable interface. It lets you believe the floor beneath you is still because, at your scale, that belief is useful. But usefulness is not the same as full truth. Beneath the calm face of every solid thing, matter is restless. A mountain that seems eternal is made of atoms vibrating. A diamond that seems perfect is made of atoms vibrating. The bones inside your body, the chair beneath you, the screen glowing in front of you, all of them are held together by patterns of motion so consistent that they appear motionless. And maybe that is the deeper lesson hidden inside this first subject. Stillness is often not the absence of movement, but movement too small, too balanced, or too constant for you to notice. The universe does not always announce its activity with storms and explosions. Sometimes it hides motion inside silence. Sometimes it builds firmness out of trembling. Sometimes the most stable thing in the room is not the thing that does not move, but the thing whose motion is so well organized that it can hold a shape. So the next time you place your hand on a wall, or rest your head on a pillow, or watch a stone lying quietly in the dust, remember that you are not touching perfect stillness. You are touching a choreography. You are touching atoms held in place but never completely asleep. You are touching a world that whispers through vibration, even when it seems to say nothing at all. Molecules move in every breath. The quietest thing you do all day is also one of the most crowded events in your body. You inhale, and it feels simple, almost empty, as if air were a soft nothing passing through you without history. But every breath is a storm of moving molecules. Invisible travelers rushing through your nose, your throat, your lungs, and finally into the delicate edges of your blood. The air around you is not a blank space waiting to be pulled in. It is a restless mixture, mostly nitrogen, with oxygen, carbon dioxide, water vapor, argon, and tiny traces of other gases, all moving in different directions at tremendous speeds. They do not wait politely at the entrance of your lungs. They collide, scatter, bounce, twist and spread, following the hidden rules of pressure and concentration. When your diaphragm pulls downward and your chest expands, the pressure inside your lungs becomes slightly lower than the pressure outside, and air flows inward. But what enters is not a smooth river. It is a chaotic crowd. Trillions upon trillions of molecules, each following its own path, each striking other molecules, each changing direction so often that its journey looks random from up close. And yet, from this microscopic disorder, your body creates one of the most stable rhythms of your life. You breathe in, you breathe out, the chaos becomes survival, the motion becomes you. Deep in your lungs, the air reaches tiny sacs called alveoli, delicate structures with walls so thin that gases can pass across them. Here, oxygen molecules do something extraordinary. They do not need a tiny hand to carry them. They do not need a pump to force them across each wall. They move because there is more oxygen in the fresh air of the lungs than in the blood arriving from the body. So oxygen diffuses across, slipping from where it is more crowded to where it is less crowded, until red blood cells capture it with hemoglobin and carry it away. At the same time, carbon dioxide moves in the opposite direction. Your cells produced it while releasing energy from food. and your blood brings it back to the lungs, where it diffuses into the air spaces and leaves with your exhale. This exchange happens quietly, without drama, every moment you are alive. A breath is not merely air entering and leaving. It is a molecular negotiation between your body and the atmosphere. You are not sealed away from the world. You are open to it. Every inhale brings part of the outside into your chemistry. Every exhale returns part of your inner life back to the room. This means the boundary between you and the world is softer than it feels. You may think of your skin as the edge of your body, but your lungs tell a deeper story. They are an enormous inner surface folded inside you, a living coastline where the atmosphere touches blood. And across that coastline, molecules are constantly moving. The oxygen in your next breath may have drifted through trees, oceans, cities, storms, fires, or ancient cycles of life and decay before reaching you. The carbon dioxide you release may one day feed a leaf, dissolve into rain, or wander through the air long after you have forgotten this moment. Breathing connects you to a planetary circulation older than language. It reminds you that life is not possession, it is exchange. You borrow oxygen for a few seconds, use it to keep your cells alive, and return what you no longer need. Even when you sit completely still, your breath is a doorway of motion. Air moves through branching passages, water vapor warms and moistens each inhale. Tiny hairs and mucus help trap dust and particles. Muscles adjust without your conscious permission. Your brainstem quietly monitors the chemistry of your blood and changes the depth or speed of breathing when carbon dioxide rises. This is why you breathe harder during exercise, not simply because your body wants more oxygen, but because it needs to remove extra carbon dioxide and keep the balance of your blood within a narrow range. Your breathing is not just a habit, it is a real-time conversation between chemistry, nerves, muscles, and air. And perhaps the strangest part is how invisible all of this feels. You can spend years breathing without noticing that each inhale is molecular traffic, each exhale a release of internal evidence, each pause between breaths a fragile balance maintained by systems you rarely thank. Stillness, here, becomes an illusion not because your body is dramatically moving, but because the molecules that keep you alive never stop. They are entering, leaving, crossing, dissolving, binding, and separating in a rhythm so ordinary that it becomes sacred only when you pay attention. So the next time you take a slow breath in the dark, do not think of it as empty air filling empty space. Think of it as the universe arriving in pieces small enough to enter you. Think of oxygen crossing a thin living wall, carbon dioxide escaping like a message from your cells, and the atmosphere briefly becoming part of your blood. You are not merely breathing inside the world. The world is moving through you, one molecule at a time. Brownian motion under a microscope. A tiny speck of dust under a microscope can expose a secret that your eyes were never meant to see. Imagine looking down into a drop of water and noticing a grain of pollen, a soot particle, or a faint little fragment drifting in the liquid. Not smoothly, not calmly, but in a restless, trembling, unpredictable dance. It jerks left, pauses, jumps right, slides forward, reverses, and shivers again, as if some invisible hand keeps tapping it from every side. At first it seems almost alive. That is exactly what made the observation so haunting when the botanist Robert Brown studied pollen grains in water in the early 19th century. He saw tiny particles moving in a strange, jittering way, and the motion did not stop. It was not a current carrying everything in one direction. It was not a living creature swimming with intention. It was something more subtle, more universal, and much harder to see directly. Later, scientists understood that the visible speck was being struck again and again by water molecules too small to observe with ordinary microscopes. The particle was not moving because it had a will. It was moving because the invisible world around it was never still. Brownian motion is the name we give to that jittering movement, but the name almost hides how powerful the idea really is. Under the microscope, you are not just watching a speck wobble. You are watching indirect evidence that matter is made of tiny moving parts. You are watching the hidden activity of molecules become large enough to disturb something visible. The small particle becomes a messenger. It does not show you the molecules themselves, but it reveals their presence through their impacts, like a curtain fluttering because of a wind you cannot see. And that is what makes Brownian motion so important. It turned invisible molecular motion into something measurable, something undeniable, something the human mind could no longer dismiss as a convenient theory. Before atoms and molecules were universally accepted, some scientists still treated them as useful ideas rather than real physical things. Brownian motion helped change that. In the early 20th century, Albert Einstein explained how the random motion of tiny particles could be understood as the result of countless uneven collisions from surrounding molecules. Not long after, Jean Perrin performed careful experiments that supported this explanation and helped convince the scientific world that atoms and molecules were not just mathematical imagination, but real ingredients of nature. This is a beautiful turning point in science because it shows how truth sometimes arrives indirectly. You do not always see the hidden cause itself. Sometimes you see a visible thing being disturbed, and from that disturbance you infer the deeper world. A tiny particle under glass becomes a doorway into the architecture of matter. The motion looks random because the particle is being hit from all sides, but not evenly at every instant. One moment, more molecules push from the left, another moment, more from below, another from the front. Each collision is small, but together they create a wandering path with no planned destination. It is not chaos in the sense of meaninglessness. It is order too complex and too crowded to appear as order at your scale. That is the quiet lesson of Brownian motion. Randomness is not always the absence of causes. Sometimes randomness is what too many causes look like when you cannot track them one by one. The speck moves because the world around it is full of microscopic events, each too tiny to notice alone, but together strong enough to shake a visible object into motion. This is why Brownian motion becomes stronger when the surrounding fluid is warmer, because warmer molecules move more actively and strike the particle more intensely. It is also why smaller particles show the motion more clearly than larger ones. A large object averages out the tiny impacts, like a heavy boat barely disturbed by small ripples. But a very small particle is light enough to be pushed around by the uneven storm. The thickness of the liquid matters too. In a thicker fluid, the particle struggles more, and its wandering slows. So what appears at first as a strange, twitching dance is actually a physical record of temperature, size, fluid resistance, and molecular activity. The microscope shows a simple image, but behind it is a whole hidden world pressing into view. And once you understand Brownian motion, you begin to see why stillness is such a human illusion. A glass of water resting on a table may look calm, but inside it, microscopic particles are being nudged from every direction. Smoke in air drifts and spreads partly because tiny suspended particles are constantly jostled. Fine dust, droplets, pigments, and microscopic biological material can wander in ways shaped by this same restless background. Brownian motion also helps explain diffusion, the gradual spreading of particles from crowded regions into less crowded ones, not because every particle knows where to go, but because random motion over time tends to scatter things outward. A drop of ink spreading through water, a scent slowly filling a room, nutrients moving through tiny biological spaces. All of these belong to a wider family of hidden motion. But what matters most is not only the science, it is what the science does to your certainty. You look at the world and your mind wants clean categories. Still or moving, alive or dead, empty or full, random or meaningful. Brownian motion quietly breaks those categories open. The speck seems alive, but it is not alive. The motion seems purposeless, but it is built from real physical causes. The water seems still, but it is crowded with collisions. The invisible seems unreachable, yet it leaves fingerprints on the visible. This is the kind of truth that changes how you look at ordinary things. It teaches you that what you cannot see may still be shaping what you can see. It teaches you that a small visible disturbance may be the shadow of a much deeper reality. And perhaps in a strange way, it teaches humility. Your senses give you the large, smooth version of the world, because that is the version you can survive inside. But under the microscope, the smooth world begins to tremble. It reveals that calm surfaces are often built on frantic interiors, that silence may be filled with collisions, that randomness may carry evidence, and that the smallest visible movement can testify to an entire invisible universe. So the next time you see dust floating in a beam of light, or ink slowly spreading in water, or a tiny particle drifting without an obvious cause, remember the lesson hidden in Brownian motion. The world does not need to show you its machinery directly. Sometimes it lets one tiny speck wander under a lens, and from that wandering, you discover that the unseen is not empty. It is active, it is real, it is touching everything. Heat as hidden motion. Heat is not a thing hiding inside an object like a secret liquid. It is the invisible restlessness of matter becoming noticeable to your body. When you hold your hands near a fire, touch a warm cup, step onto sunlit pavement, or feel your phone grow hot after hours of use, your senses tell you that something called heat has arrived. It feels like a substance, almost like warmth is pouring into your skin. For centuries, even scientists imagined heat this way, as if it were a special fluid that flowed from hotter things into colder ones. But the deeper truth is stranger and more beautiful. Heat is not a material being added to matter. Heat is energy being transferred because countless tiny particles are moving, colliding, rotating, vibrating, and passing their agitation along. A hot object is not filled with magic fire. Its microscopic parts are more energetically restless than the microscopic parts of a colder object. When you touch it, that hidden motion begins to disturb the particles in your skin, and your nerves translate that disturbance into the feeling you call warmth. This is why heat feels intimate, almost emotional, even though it is physical. It is motion crossing a boundary. It is one system sharing its restlessness with another. Imagine a quiet crowd standing shoulder to shoulder, and then one corner of the crowd begins to jostle. The pushing spreads from person to person, not because anyone is carrying an object called heat, but because motion is being handed along. That is close to what happens in conduction. When a hot pan warms its handle, or a spoon left in soup slowly becomes too hot to hold. Energy moves through matter as particles interact with neighboring particles. And in metals, this happens especially well because some electrons can help carry energy through the material quickly. This is why a metal spoon heats faster than a wooden one in the same pot. It is not that metal loves heat more. It is that its internal structure is better at passing microscopic energy along. But heat does not move in only one way. It can travel through moving fluids, where warmer regions become less dense and rise while cooler regions sink, setting up circulation. It can also cross empty space as infrared radiation, which is why sunlight can warm your face even after traveling through the vacuum between the sun and Earth. That alone should make you pause. Warmth can reach you by touch, by flow, or by light you cannot see. The comfort of a blanket, the burn of a stove, the glow of a campfire, the warmth of another person beside you, all of them are different expressions of energy moving from one arrangement into another. And yet temperature and heat are not exactly the same thing. Temperature tells you something about the average microscopic energy within a substance, but heat describes energy in transit, energy moving, because there is a difference. A bathtub full of warm water can contain far more internal energy than a tiny spark, even if the spark is much hotter, because the amount of matter matters. This is why a small flame can be extremely hot, but not warm an entire room quickly, while a large radiator at a lower temperature can slowly fill the air with comfort. Your body understands this difference without using words. A brief touch of something very hot can burn a small patch of skin, while sitting in a mildly warm room changes your whole state gradually. Heat is not only intensity, it is scale, contact, duration, and transfer. It is also why sweating cools you. When sweat evaporates, faster moving molecules are more likely to escape from the liquid surface, carrying energy away with them. What remains on your skin is, on average, less energetic, and your body feels cooler. The The same principle helps explain why alcohol feels cold as it evaporates quickly, why a breeze can make you feel cooler by removing warm, moist air near your skin, and why stepping out of water can chill you even on a warm day. Cooling is not the arrival of cold as a substance. It is the removal or redistribution of energy. Cold is often the sensation of your body losing microscopic motion faster than it can replace it. This turns ordinary experience into something quietly astonishing. A warm mug is a battlefield of energy exchange. Ice in a drink is not sending cold into the liquid. The drink is giving energy to the ice, loosening its structure until it melts. A fever is not merely a number on a thermometer. It is your body changing its thermal conditions as part of a biological response. Friction warms your hands when you rub them together, because organized motion is being transformed into disordered microscopic motion. The motion you can see becomes motion you can feel but cannot see. That is one of the deep lessons of heat. Energy does not vanish when the visible movement stops. It changes form. It hides inside the microscopic world. A car braking, a meteor entering the atmosphere, a drill bit cutting into metal, a rope sliding too quickly through your hand, all reveal the same truth. Large-scale motion can dissolve into countless small-scale motions, and your skin calls that transformation heat. This is also why heat has a direction in everyday life. Left alone, energy tends to spread out. A hot cup cools in a room because its concentrated thermal energy disperses into the surrounding air, table, and environment. The reverse does not happen naturally in the same simple way. You do not see a lukewarm cup suddenly steal scattered energy from the room and become boiling hot by accident. This directionality gives time a texture. It is one reason the world feels like it moves from usable difference toward balance. Heat teaches you that the universe is always trying to even out its hidden motions, to smooth sharp differences, to turn gradients into gentler states. And maybe that is why warmth feels so human. Your body is always balancing it, producing it, losing it, protecting it. Too little, and life slows into danger. Too much, and proteins, cells, and organs begin to fail. You live inside a narrow thermal window, a fragile agreement between your chemistry and the world. Every comfortable room, every blanket, every shade tree, every sip of warm tea is part of that agreement. So the next time you feel heat, do not imagine it as a simple glow or a mysterious fluid. Imagine motion becoming touch. Imagine invisible energy moving through matter, air, light, and skin. Imagine the world constantly sharing its restlessness, spreading it, transforming it, hiding it beneath surfaces that look calm. Warmth is not separate from motion. Warmth is motion translated into feeling. And perhaps that is the quiet wonder of it. Even when the world seems still, its hidden movements are already reaching you, entering your nerves, shaping your comfort, warning you of danger, and reminding you that to feel heat is to feel the microscopic life of matter brushing against your own. Absolute zero and its limits. The coldest place possible is not a place you can walk into, but a boundary the universe refuses to let you fully touch. Absolute zero sounds like the final silence of matter, the point where everything simply stops, where atoms give up their motion and reality becomes a frozen photograph. But the truth is more interesting and more unsettling, because absolute zero is not just extreme cold. It is a limit built into the way physical systems work. It is 0 Kelvin, equal to minus 273.15 degrees Celsius, and it represents the lowest temperature allowed on the ordinary temperature scale. At that point, a system has as little thermal energy as it can have, not less, not nearly less, the bottom. And yet, this bottom is not something scientists can simply reach by making things colder and colder forever. It is more like a horizon. You can move toward it with astonishing precision, closer and closer, using some of the most delicate technology ever built, but every step becomes harder than the last. The closer matter gets to absolute zero, the more stubborn it becomes, as if cold itself turns into a locked door. This is one of the great surprises of physics. The universe has a lowest possible temperature, but reaching it exactly appears impossible by any finite physical process. Scientists call this idea part of the third law of thermodynamics, and behind the formal language is a deeply simple picture. Cooling something means removing energy from it. At ordinary temperatures, that is easy enough. A hot drink cools because energy flows into the surrounding air. A freezer cools food by moving energy out of it. But when an object becomes extremely cold, there is less and less removable thermal energy left, and the final traces become harder to extract. It is like trying to dry a sponge that already feels dry, then trying to remove the last invisible moisture trapped deep inside its fibers. Each attempt removes less. Each improvement demands more control. At some point, cooling is no longer just making something cold. It becomes a battle against every tiny leak of energy from light, vibration, magnetic fields, surrounding walls, even the measuring instruments used to observe the system. The laboratory must become a kind of shielded world, isolated from warmth, noise, and disturbance. And still, absolute zero remains just out of reach. This is not because scientists are careless or because the equipment is not advanced enough. It is because the laws themselves seem to turn absolute zero into an unreachable endpoint, a perfect stillness that can be approached but not possessed. And what happens near that endpoint is stranger than ordinary coldness. Materials can stop behaving like the familiar substances you know. Certain metals can become superconductors, allowing electrical current to flow without ordinary resistance. Some liquids can become superfluids, moving with almost impossible smoothness. Clouds of atoms can begin acting less like separate particles and more like one shared quantum state. These are not magical effects. They are what happens when thermal disorder is reduced so much that deeper rules become visible. At room temperature, heat is noisy. It shakes, blurs, and overwhelms subtle behavior. But as temperature falls, the noise quiets, and matter begins to reveal hidden forms of organization. Cold, then, is not merely the absence of warmth. It can be a microscope for reality. It can uncover behaviors that are normally buried beneath thermal agitation. That is why scientists chase temperatures close to absolute zero, not just to break records, but to see nature with fewer distractions, to study atoms when they are slow enough to control, to build better atomic clocks, to explore quantum states, to test the boundary between the familiar world and the strange rules beneath it. Yet this pursuit also teaches humility, because the phrase absolute zero can mislead the imagination. It tempts you to picture a dead universe where nothing happens at all. But physics is careful here. Absolute zero is the lowest possible temperature, not a simple button that turns existence off. Even at the lowest energy state allowed to a system, matter is not necessarily the cartoon of perfect classical stillness. The deeper quantum world does not behave like a tiny machine that can be brought to complete rest in the old-fashioned sense. That full story belongs to the strange idea of ground states and residual quantum behavior, but for now, the important lesson is this. Temperature measures a certain kind of energy, not every kind of existence. Absolute zero removes thermal disorder as far as nature allows, but it does not give you a universe made of nothing. It gives you a universe stripped down to its lowest permitted condition. And that distinction matters because it changes the emotional meaning of cold. Cold is not simply emptiness. It is not simply death. It is reduction, simplification, the removal of noise until hidden structure begins to stand out. Imagine a room after every conversation has faded, every footstep has stopped, every light has dimmed, and in that silence, you suddenly hear the faintest clock inside the wall. Extreme cold is like that. It quiets the loud motions so the subtle ones can be studied. It turns matter into a calmer instrument, but the final silence remains unreachable. There is always another barrier, another limit, another reason why perfect stillness slips away. And perhaps that is the most beautiful part. Absolute zero tells you that the universe allows the idea of a final boundary, but not the easy possession of it. You can move towards silence, but silence has depth. You can move towards stillness, but stillness is not as simple as it looks. You can cool matter until it becomes almost unimaginably quiet, and still nature keeps one last secret behind the door. So when you hear the phrase absolute zero, do not imagine only a number, or a frozen laboratory, or a world where everything has ended. Imagine a horizon at the bottom of temperature, a place physics can point toward but never casually enter. Imagine scientists approaching it like explorers approaching the edge of a dark ocean, lowering the noise of matter until strange new patterns appear. And then ask yourself, what else in life works this way? The closer you get to perfect calm, perfect certainty, perfect silence, the more you discover that perfection is not a destination you conquer, but a limit that teaches you how deep reality goes. 0-point motion. Even when nature has been cooled to its quietest possible state, something inside it still refuses to become perfectly still. This is the strange lesson of 0-point motion, one of those ideas that sounds like a contradiction until you realize it is not describing ordinary movement at all. In the familiar world, rest seems simple. A ball can sit on the floor, a stone can lie in the dirt, a machine can be switched off. But the quantum world does not allow that kind of perfect pause for tiny bound things like atoms inside a material or particles trapped in a small region. When a particle is confined, when it is held in a limited space by forces around it, it cannot have both a perfectly fixed position and a perfectly fixed motion. This is not because our instruments are clumsy or because we have not looked carefully enough. It is built into the structure of quantum reality. The particle is not a tiny bead that simply failed to calm down. It is described by a spread out quantum state, a kind of probability pattern, and that pattern cannot shrink into absolute certainty without consequences. So even in the lowest possible energy condition of that system, a subtle motion remains. This leftover activity is called 0-point motion. The name sounds technical, but the image is simple. It is the motion that remains when all removable thermal agitation has been stripped away, the final trembling that belongs not to heat, not to disturbance, not to outside noise, but to the quantum rules themselves. Imagine trying to hold a note on a violin string so gently that it becomes completely silent, yet discovering that the string still carries a faint, unavoidable hum, because its very nature will not let it become a deadline. That is not a perfect analogy, but it points toward the feeling of the idea. 0-point motion is not matter being careless. It is matter obeying a deeper law. You can see its importance in the behavior of real substances. Helium, for example, is famously difficult to freeze under ordinary pressure, even when cooled extremely close to the lowest temperatures possible. Its atoms are so light and their quantum motion is so significant that they keep resisting the fixed arrangement of a normal solid unless extra pressure is applied. This does not mean helium is magically warm. It means the atoms still possess quantum motion, even when ordinary thermal motion has been reduced almost as far as it can go. That single fact should change how you imagine cold, matter, and stillness. The deepest quiet is not emptiness. It has rules. It has a minimum shape. It has a motion that cannot be removed by patience alone. 0-point motion also affects the tiny vibrations of atoms in solids, the stability of molecules, and the behavior of materials at extremely low temperatures. In chemistry, the lightest atoms, especially hydrogen, can show strong quantum effects because their small mass makes their 0-point motion more noticeable. This can slightly change bond lengths, reaction behavior, and the way different isotopes act, because heavier versions of the same element tend to have less 0-point motion than lighter ones. That may sound like a small detail, but science often advances through details that reality refuses to hide. A molecule is not a rigid sculpture. Its atoms occupy allowed quantum patterns, and even in the lowest pattern, they do not become perfectly motionless points. Their positions have a subtle uncertainty, a built-in softness. In this sense, 0-point motion is one reason the microscopic world never becomes the hard mechanical clockwork people once imagined. It has structure, yes. It has laws, yes. But it also has a kind of irreducible looseness, a refusal to be pinned down completely. And this is where the idea becomes quietly profound. You might think the deepest layer of physical reality would be the most certain, the most locked, the most obedient. Instead, when you go downward, you find limits to certainty itself. You find that perfect rest is not always a physical option. You find that what looks like stillness from the outside may contain a final hidden activity that exists simply because confinement and quantum behavior demand it. This is not an excuse to invent mystical claims, and it is not a source of unlimited energy waiting to be harvested. Zero-point motion cannot be treated like a free battery that anyone can drain without changing the system. It is part of the lowest energy condition available to that system, not a casual reservoir of usable motion. That distinction matters, because the truth is already fascinating without exaggeration. Nature does not need false miracles. The real one is enough. Even at the bottom of ordinary cooling, matter does not become a frozen cartoon. It enters its lowest allowed quantum state, and that state still has life in it. Not biological life, not conscious life, but physical restlessness woven into the rules of existence. Think about how strange that is. The universe seems to say that no matter how carefully you remove noise, no matter how deeply you quiet a system, there remains a final whisper that belongs to being itself. Not the loud motion of heat, not the visible motion of objects, not the drifting of dust or the rush of air. Something more fundamental, more private, more difficult to imagine. A motion that is not added from outside, but written into the way small things can exist when they are held in place. So when you picture the microscopic world, do not picture tiny objects finally settling into perfect sleep. Picture them reaching the calmest state they are allowed to have, and still carrying a faint, unavoidable pulse. That pulse is a reminder that reality is not built from dead pieces waiting to be arranged. It is built from patterns that remain active even in their quietest form. And perhaps that is the most unsettling beauty of zero-point motion. At the deepest edge of stillness, nature does not give you nothing. It gives you the smallest possible unrest, the quiet motion that remains when every louder motion has disappeared. Quantum ground states. A quantum system does not fall into perfect emptiness when it becomes as calm as it can be. It settles into a lowest allowed pattern, and that pattern quietly decides what matter is allowed to become. This is what physicists call a ground state, the most stable state a quantum system can occupy, the bottom floor of its possible behavior, the condition it returns to when it has given away every extra bit of energy it can release. But this bottom is not like a ball resting at the lowest point of a bowl in the ordinary world. In classical thinking, if something loses enough energy, you imagine it simply stops. In quantum physics, the ground state is stranger. It is not a dead point, it is a permitted arrangement, a shape of possibility, a lowest energy pattern that follows the rules of the system. An atom, a molecule, a crystal, even a field can have a ground state, and that ground state is not chosen randomly. It is determined by the forces acting inside the system, and by the quantum rules that limit what forms are allowed. Think of a musical instrument. A guitar string cannot vibrate in just any shape it wants. It has natural ways of resonating, natural patterns it can hold. Some are higher, more energetic, more excited. One is the lowest note it can produce in that setup. A quantum ground state is something like that lowest note, except it belongs not to sound, but to matter itself. It is nature saying, "This is the quietest form this system can take without ceasing to be what it is." And this idea is not just abstract. It is one of the reasons atoms are stable. If the old picture of the atom were completely true, with electrons moving like tiny planets around a nucleus, then electrons should lose energy and spiral inward, collapsing into the center. Matter would not last. Chemistry would not work. Your body, the Earth, every object around you would be impossible. But quantum physics changes the story. Electrons in atoms occupy allowed states, and the lowest of these is a ground state. Once an electron is in that lowest state, it cannot simply fall lower, because there is no lower allowed state available within that atom. The ground state becomes a kind of protection. Not a wall made of stone, but a rule made of structure. It gives matter a floor beneath its feet. When atoms absorb energy, their electrons may move into excited states, higher allowed patterns. But those excited states are usually temporary. The atom tends to return toward its ground state, and when it does, it releases the extra energy, often as light. This is one of the hidden reasons the universe glows in such specific colors. A neon sign, a street lamp, the spectral fingerprints of distant stars, even the light used in many scientific instruments all depend on atoms and molecules shifting between allowed states. They do not emit every possible color smoothly. They release energy in particular steps, because their internal states are not a continuous staircase, but a set of allowed levels. The ground state is the anchor of that staircase, the reference point from which excitation and return make sense. In molecules, the ground state helps determine shape and bonding. It influences how atoms settle together, how stable a molecule is, how it reacts, how it absorbs light, how it stores and releases energy. The calmest arrangement is not always simple. For a complex molecule, finding the ground state can be incredibly difficult, because there may be many ways for its electrons and nuclei to arrange themselves, many competing possibilities, many nearly stable patterns. Nature does not solve this like a person doing a calculation on paper. It simply behaves according to its laws, and the system settles into whatever arrangement those laws permit as lowest. This is why ground states matter in chemistry, materials science, and modern technology. The color of a material, the behavior of a semiconductor, the magnetism of certain solids, the strange properties of ultra-cold systems, all depend on how their quantum ground states are organized. Even when nothing dramatic appears to be happening, the ground state is quietly setting the rules. It is the hidden default from which the visible world begins. But there is another subtle lesson here. The ground state is not always unique in a simple way. Sometimes a system can have more than one arrangement with the same lowest energy, like a valley floor with several equally low places to stand. In those cases, the system may choose one pattern among several, and that choice can shape large-scale behavior. This is connected to deep ideas in physics, including symmetry, magnetism, and phase transitions. But you do not need heavy mathematics to feel the significance. The lowest state of a system is not always a single silent answer. Sometimes it is a set of possible quiet answers, and the one that becomes real can change the form of matter. That should make you see rest differently. Rest is not the absence of structure. Rest is structure at its most economical. Rest is the universe taking the least costly shape it can take under the rules it has been given. When a system is in its ground state, it is not lazy, it is precise. It has settled into a deep agreement between energy, force, and possibility. And perhaps that is why the idea feels strangely reflective. You are used to thinking of calm as emptiness, as nothing happening, as a blank surface. But quantum ground states reveal a different kind of calm, one that is rich with form. The quietest version of a thing may be the version where its deepest rules are most clearly expressed. A hydrogen atom in its ground state is not doing nothing. It is being hydrogen in the most stable way it can. A molecule in its ground state is not meaningless because it is unexcited. It is holding the arrangement from which its chemistry begins. A material in its ground state is not merely cold or passive. It is carrying the blueprint of its properties. And this invites a deeper question. How much of what you call stillness is actually a hidden form of order? How much of what looks inactive is really a system resting inside its most faithful pattern? The ground state teaches that reality does not need constant drama to be profound. Sometimes the deepest truth is not found in explosions, collisions, or visible movement, but in the quiet minimum that makes everything else possible. So when you hear the phrase ground state, do not imagine an empty basement beneath reality. Imagine the first note in a cosmic instrument, the lowest permitted tone from which every higher song begins. Imagine matter returning to its most stable self after disturbance. Imagine atoms, molecules, and materials carrying invisible flaws beneath their behavior, flaws that prevent collapse, shape light, guide chemistry, and give the world its steady presence. And maybe, as you listen, you begin to feel the soft lesson inside the science. Calm is not nothingness. Calm can be structure. Calm can be law. Calm can be the hidden foundation that lets the universe keep its shape. Electrons do not sit still. The electron is one of the reasons matter does not behave like a tiny mechanical toy, because the closer you try to picture it sitting somewhere, the more the picture falls apart. You were probably once shown an atom as a miniature solar system, with a nucleus in the center and electrons circling around it like planets around a sun. It is a useful drawing for children, but it is not the real image. Electrons do not sit in neat little chairs around the nucleus. They do not follow clean circular tracks like beads on invisible wires. They do not wait patiently in one place until something pushes them. An electron in an atom is better understood as a quantum presence, a spread of possibility around the nucleus, shaped by energy, attraction, and the rules of quantum mechanics. That sounds strange because your everyday mind wants every object to have a definite location. A coin is on the table, a bird is in the tree, a stone is on the ground, but an electron is not a small coin hidden somewhere inside the atom. When it belongs to an atom, it exists in what scientists call an orbital, which does not mean an orbit like a planet, but a region where the electron is likely to be found if measured. Before measurement, the electron is described by a pattern, not by a tiny dot following a secret path. This is why saying electrons do not sit still is not just saying they move very fast. It is saying something deeper. Their existence is not the kind of existence that can be frozen into a simple still picture. They are not little balls buzzing around because they are restless in the ordinary sense. They are quantum objects, and quantum objects do not obey the same rules as dust, sand, or planets. Their motion is tied to wave-like behavior, energy states, and uncertainty. If you try to force the electron into a perfectly fixed position, you disturb the very state you are trying to describe. Nature does not let you know everything about such a small thing with perfect sharpness. The electron's position and motion cannot both be nailed down like details on a police report. This is not a weakness in human knowledge. It is part of the way the world is built. And because electrons do not simply sit still, atoms have structure. Chemistry exists. Light can be absorbed and released. Materials can conduct electricity, reflect color, store energy, form bonds, and build the complexity of your body. In atoms, electrons occupy allowed energy states. When they absorb energy, they can shift to higher states, and when they fall back to lower ones, they can release light of specific colors. This is why neon signs glow, why fireworks display different colors depending on their ingredients, why astronomers can study the composition of distant stars by reading the dark and bright lines in their light. The electron's refusal to behave like a stationary speck is written across the universe in color. Every glowing gas, every spectral fingerprint, every chemical bond whispers the same message. Matter is not built from still pieces arranged like furniture. It is built from active quantum patterns. Electrons also explain why atoms do not simply collapse. The negatively charged electrons are attracted to the positively charged nucleus. So in a purely old-fashioned picture, you might expect them to fall inward, but they do not. The quantum rules allow certain stable states, and the electrons occupy those states instead of crashing into the center. Matter remains spacious, structured, and stable because electrons are not classical particles dropping into a well. They create the outer behavior of atoms. They determine how atoms approach each other, whether they bond, whether they repel, whether they share, steal, or exchange influence. The hardness of a table, the softness of skin, the transparency of glass, the conductivity of copper, the sparkle of a diamond, and the chemistry of a living cell all depend on electrons arranged in these strange, non-still ways. And in metals, some electrons are not tightly bound to one atom. They can move through the material more freely, which is why electric current is possible. But even here, the reality is not a simple stream of tiny pellets racing through a wire at the speed of light. The signal that organizes the current travels quickly through the electric field, while the individual electrons drift much more slowly through the material. That detail matters because it shows again how misleading simple pictures can be. When you flip a switch and a lamp turns on almost instantly, it is not because one electron from your finger rushed all the way to the bulb like a messenger sprinting down a tunnel. The whole electromagnetic system responds, and countless electrons in the wire begin adjusting together. Electricity is not just little things moving. It is matter and fields coordinating in a way your senses cannot directly see. Even in the circuits inside your phone, your computer, your nervous system's electrical signals, The deeper story is electron behavior shaped by materials, barriers, energy levels, and interactions. The modern world is built on learning how electrons refuse to sit still in predictable classical ways. Transistors, LEDs, solar panels, lasers, batteries, medical imaging, and countless sensors depend on controlling electron states and movements with astonishing precision. You are surrounded by technologies that work because scientists stopped imagining electrons as tiny planets and began treating them as quantum entities with allowed states, probabilities, and wave-like behavior. That should make the ordinary world feel less ordinary. The screen you look at is a controlled dance of electron behavior. The colors appearing before your eyes are made possible by energy changes and material responses. The battery powering it stores energy through chemical arrangements that depend on electrons shifting between atoms and molecules. Even the nerves carrying sensations through your body rely on charged particles and electrical differences across membranes, systems that ultimately depend on the same deep rules of charge and interaction. And yet, the electron itself remains strangely resistant to simple visualization. You can measure its effects with incredible accuracy. You can predict its behavior in many situations with astonishing success. You can build civilization around its properties, but you cannot honestly turn it into a tiny marble sitting somewhere inside reality. That is the humbling beauty of it. Some of the most real things in the universe are not easy to imagine. They are known through patterns, effects, measurements, and consequences. The electron is real not because you can picture it perfectly, but because the world cannot function without it. It shapes atoms, chemistry, light, electricity, and life. It helps decide what matter can be. So when you hear that electrons do not sit still, do not imagine only frantic movement. Imagine a deeper refusal. A refusal to be reduced to a frozen dot. A refusal to behave like the objects your hands can hold. A refusal that makes the visible world possible. The still chair beneath you. The quiet wall beside you. The dark room around you. The soft glow of a screen in the night. All are built from electrons that are not sitting like stones in tiny places. They are occupying patterns, responding to forces, forming bonds, carrying charge, releasing light, and shaping the edges of what you call solid reality. And perhaps this is the quiet lesson hidden in the electron. The universe does not need to be easily pictured to be deeply real. Sometimes the foundation of everything is not a little object at rest, but a restless rule, a living probability, a hidden pattern that never sits still long enough for your imagination to trap it. Fields fluctuate in empty space. The emptiest space you can imagine is not truly empty. It is a quiet surface hiding a restless depth. Picture a dark room with all the air removed, all dust gone, all light blocked, all ordinary matter taken away until nothing remains that your senses would recognize. You might expect perfect blankness, a kind of cosmic silence with no texture and no activity. But modern physics tells a stranger story. What we call empty space is not a dead background. It is filled with fields, and those fields are not optional decorations added to the universe. They are the underlying systems from which particles and forces emerge. An electron is not simply a tiny object floating in space. It is connected to an electron field. Light is connected to the electromagnetic field. Other particles belong to other fields. And even when there are no particles present in a region, the fields themselves still exist. This is the first shock. Removing particles does not remove the stage on which particles can appear. The field remains, spread through space, carrying the possibility of activity. In quantum physics, a field cannot be perfectly motionless in the old classical sense, because the rules do not allow every property to be sharpened into total certainty at once. So even the lowest state of a field has a kind of subtle unrest. Physicists call these vacuum fluctuations, but the phrase can easily mislead you. It does not mean empty space is literally boiling with tiny solid balls popping in and out like cartoon sparks. That image is dramatic but too simple. A better way to think of it is this. The value of a quantum field in empty space is never a perfectly flat, frozen line. It has unavoidable uncertainty. It trembles in a deeply mathematical, physical sense, not because something is shaking it from outside, but because quantum fields cannot be completely pinned down. The vacuum is therefore not a blank nothing. It is the lowest energy condition of the fields, and even that condition carries fluctuations. This matters because these fluctuations are not just philosophical decoration. Their effects can be measured. One famous example is the Casimir effect, where two very close metal plates in a vacuum can experience a tiny attraction, because the allowed fluctuations of the electromagnetic field between the plates differ from those outside. The plates are not pulled together by ordinary wind, air pressure, or hidden glue. They reveal that the vacuum itself has structure, that the conditions of empty space can change depending on boundaries. Another example appears in the fine details of atomic energy levels, where the interaction between charged particles and vacuum fluctuations slightly shifts the behavior of atoms. These effects are small, but small does not mean imaginary. In physics, sometimes the quietest signals are the most powerful, because they show that nature is active even where common sense expects absence. This is where the idea becomes deeply unsettling. You grew up thinking of nothing as simple. A cup can be empty, a room can be empty, a road can be empty, but those are human kinds of emptiness. They mean empty of the things we care about, empty of objects large enough to notice, empty of furniture, people, air, light, or sound. Physics asks a harsher question. What remains when you remove everything removable? The answer is not ordinary nothing. The answer is fields, laws, possibility, and a lowest state that still refuses to become perfectly featureless. Empty space is not a hole in reality. It is part of reality. It has properties. It can stretch, carry radiation, allow forces to act, shape particles, and respond to boundaries. The vacuum is closer to a silent ocean than to an empty box. You may not see waves on its surface, but its depth is not gone. And yet we must be careful. This does not mean every wild idea about free energy or endless power from the vacuum is true. Vacuum fluctuations are real, but they are not a simple fuel tank waiting for anyone to drain. The fact that empty space has quantum activity does not give us unlimited usable energy. The universe is subtler than that. Its strangeness is not a permission slip for fantasy. The real truth is already astonishing enough. The most stripped-down version of space still has a kind of hidden liveliness. This changes the emotional shape of emptiness. Instead of thinking of empty space as a void where reality disappears, you can think of it as the quiet foundation beneath visible things. Particles are excitations of fields, like ripples rising from a surface that was already there. Forces are not spells acting across dead nothingness, but relationships carried by fields that fill the universe. Even the darkness between stars is not pure absence. It is crossed by fields, radiation, gravity, quantum uncertainty, and the quiet potential for things to happen. You are not living in a universe made of objects placed inside nothing. You are living inside a continuous physical fabric whose calmest state is still not perfectly silent. And maybe this is why the idea feels so haunting. Human beings often fear emptiness because it seems like erasure, like loss, like meaning removed. But the vacuum teaches a different lesson. Emptiness is not always the opposite of presence. Sometimes emptiness is the hidden condition that makes presence possible. The field must exist before the particle can appear. The quiet background must exist before the visible event can rise. The silence must exist before the note can be heard. So when you look into the dark spaces between things, do not imagine that reality has ended there. Imagine fields extending through the darkness, subtle fluctuations breathing beneath measurement, a lowest state that still carries tension and possibility. Empty space is not nothing wearing a mask. It is something too quiet for your senses, too deep for ordinary language, and too fundamental to ignore. And perhaps that is the final wonder. Even when the universe seems to give you emptiness, it is not offering a blank page. It is offering the invisible paper on which everything else is written, vacuum energy at the smallest scale. The smallest emptiness in the universe may carry one of the biggest unsolved problems in all of science. When you imagine a vacuum, you probably imagine a region where everything has been removed. No dust, no air, no light, no particles drifting through the dark. But physics does not treat the vacuum as a simple absence. At the deepest level we understand, space is associated with quantum fields, and those fields have a lowest possible condition. That lowest condition is not the same as ordinary nothing. It can carry what physicists call vacuum energy, a baseline energy linked to the quantum nature of fields themselves. This idea sounds almost impossible at first, because energy usually feels like something active, something attached to motion, heat, light, pressure, or work. How could empty space have energy if there is nothing inside it to move? The answer begins with the fact that quantum fields are not like empty containers waiting for particles to enter. They are more like the basic fabric from which particle behavior arises. In many quantum descriptions, each field can be thought of as having many possible ways to be excited. And even when those excitations are absent, the field still has a lowest state. That lowest state can contribute energy. Not energy in the familiar sense of a flame burning, a battery draining, or a moving object crashing into another, but energy as part of the ground-level condition of the field. This is where the subject becomes both real and dangerous to simplify. Vacuum energy is not a hidden reservoir that a machine can easily tap for endless power. It is not a magical fuel beneath space. It is not proof that nothing creates something in the casual way people sometimes say online. It is a serious, subtle idea inside quantum field theory, and its most fascinating feature is not that we fully understand it, but that we do not. In ordinary quantum calculations that do not include gravity, scientists can often ignore the absolute value of vacuum energy and focus on changes or differences, because many measurable effects depend on differences rather than on the total baseline. But gravity changes the story. In Einstein's theory, energy is not merely something objects possess. Energy influences the curvature and behavior of space-time. So if empty space truly has an energy density, then it should matter for the universe as a whole. It should gravitate. It should help determine how space expands. And this is where one of the deepest tensions in modern physics appears. When physicists try to estimate the vacuum energy suggested by quantum fields in a straightforward way, the result can become enormously larger than the vacuum-like energy we infer from cosmology. The observed accelerated expansion of the universe can be described using something called a cosmological constant, often associated with dark energy, and its value is incredibly small compared with naive quantum estimates. The mismatch is not a small rounding error. It is one of the most famous and embarrassing gaps between two otherwise successful theories. Quantum field theory works beautifully for particles and forces at small scales. General relativity works beautifully for gravity and the large-scale universe. But when the question becomes, how much should empty space weigh, the answers do not fit together naturally. This is known as the cosmological constant problem, and it is not just a technical puzzle. It is a crack in our picture of reality. It suggests that either we do not understand vacuum energy correctly, or we do not understand how it couples to gravity, or some deeper principle cancels most of it, hides it, balances it, or makes the naive calculation the wrong question. No one knows the final answer. That uncertainty is not a weakness to hide. It is the honest edge of knowledge. And it should make the subject feel even more profound, because here, at the smallest scale, in what seems like the simplest possible state, the universe refuses to become simple. The vacuum becomes a meeting place between the microscopic and the cosmic. Something associated with the lowest state of fields may also be connected to the fate of galaxies drifting apart. The tiny and the enormous touch each other through the question of empty space. Imagine that. The darkness between atoms and the darkness between galaxies may be linked by the same unresolved mystery. But we must walk carefully. Dark energy is the name we give to whatever is driving the accelerated expansion, and a cosmological constant behaves like a steady energy of space itself. Vacuum energy is one possible way to think about that, but the connection is not fully solved. It may be that dark energy really is vacuum energy in some refined sense. It may be that it comes from something else, such as a field changing slowly over cosmic time. It may be that our understanding of gravity must be adjusted on the largest scales. The facts are clear enough to be fascinating, but not complete enough for false certainty. This is the balance science asks of you. Wonder without exaggeration, curiosity without pretending the mystery is finished. At the smallest scale, vacuum energy also changes the way you think about emptiness. Human emptiness is usually defined by what is missing. An empty room has no people. An empty bowl has no food. An empty road has no cars. But physical emptiness is not merely nothing we care about. It has a structure defined by laws. It has a lowest condition. It has fields. It has a relationship with measurement, boundaries, and perhaps gravity itself. Even the word empty becomes a human shortcut, a label placed over something far deeper than our senses can directly grasp. The vacuum is not crowded in the ordinary way, but neither is it meaningless. It is not a stage made of nothing. It is the quiet rule set underneath the appearance of things. And perhaps the most unsettling part is that this rule set may carry a number so small on cosmic scales, and yet so difficult to explain from microscopic theory that it seems almost delicately chosen. Too much vacuum energy, and the universe could have expanded too violently for galaxies, stars, planets, and life to form. Too little or differently signed, and the cosmic story might have unfolded in another way. This does not automatically prove design, purpose, or intention, but it does force you to ask why the universe has the balance it has. Why is empty space not overwhelming everything? Why is the large-scale acceleration gentle enough that structure had time to arise? Why do the equations that work so well in their own domains become so uneasy when asked to describe the energy of nothing? These are not small questions. They are the kind of questions that make physics feel less like a finished textbook and more like a lantern lowered into a deep well. You can see some distance downward. You can measure echoes. You can map the walls near the top, but the bottom remains hidden. So when you hear vacuum energy at the smallest scale, do not picture a glowing substance hidden inside darkness. Picture a profound accounting problem written into the foundation of reality. Picture quantum fields in their quietest condition, gravity asking what that quietness weighs, and cosmology answering with a number we can observe but not yet fully explain. Picture empty space not as nothing, but as the most mysterious kind of something, calm enough to look blank, deep enough to shape the future of the universe. And as you sit there, breathing in a room that feels ordinary, surrounded by walls, air, light, and silence, remember that beneath every visible object and between every distant star, there may be a question still open at the root of physics. The universe is not only mysterious where it is loud, bright, and violent. Sometimes its greatest mystery is hidden in the place we once called empty. The Earth rotates beneath you. You are being carried through space right now by a planet turning beneath you, and the only reason it feels still is because everything around you is moving with it. The floor under your feet, the chair beneath your body, the walls around you, the air in the room, the clouds above your roof, the oceans, forests, cities, deserts, and mountains are all part of a rotating world. Earth completes one rotation roughly every 24 hours, and that rotation is the hidden engine behind the simple rhythm you call day and night. You do not feel the planet spinning because you are not standing outside the motion watching it happen. You are inside the system, carried along with it, like a passenger on a smooth train who forgets the train is moving until something outside reveals the motion. At the equator, Earth's surface moves eastward at more than 1,600 kilometers per hour, while near the poles, the surface moves much more slowly because the circle being traveled is smaller. Yet no great wind tears you backward. No dizzy force throws you into the sky, because the atmosphere is largely rotating with Earth too. You, the ground, and the air are sharing the motion. This is why stillness feels convincing. Your body measures changes, jolts, accelerations, vibrations, not constant shared motion. If everything near you is moving together, your senses translate the experience into calm. But the calm is not proof of rest. It is proof that you are moving too smoothly to notice. And Earth's rotation is not just an invisible fact stored in astronomy books. It shapes your entire life with quiet precision. Sunrise is not the sun climbing upward around you in the old intuitive sense. It is your side of Earth turning into sunlight. Sunset is not the sun leaving you. It is your location turning away. Night is the shadowed half of the planet carrying you through darkness until rotation brings you back into light again. Every morning is not simply light arriving. It is your part of the world being rotated toward a star. That thought should make the ordinary feel enormous. When you stand at a window at dawn, you are not watching the sky change like a painted ceiling. You are riding a sphere that is turning you into the path of sunlight. The whole horizon is a moving edge. The sky seems to rotate above you because the ground below you is rotating beneath the stars. This is why, over a long exposure photograph, stars appear to draw circles around the sky, especially around the celestial poles. The stars are not actually racing around Earth each night. That apparent wheel is the shadow of Earth's own spin projected onto the heavens. One of the most elegant proofs of this rotation is the Foucault pendulum, a long swinging pendulum that slowly appears to change the direction of its swing over time. The pendulum is not being mysteriously twisted by hidden hands. It tends to keep swinging in the same plane while Earth rotates underneath it. To someone standing on the ground, the swing seems to drift, revealing the planet's motion in a quiet, almost hypnotic way. It is one of those rare experiments where you can watch the Earth move without leaving the room. Rotation also helps shape the planet itself. Earth is not a perfect sphere. It is slightly wider at the equator than from pole to pole, partly because rotation creates an outward effect strongest around the equator. Over geological time, the planet's material responds to this turning, and Earth becomes a slightly flattened sphere, a body marked by its own spin. Rotation also influences winds and ocean currents through the Coriolis effect. Moving air and water do not travel over a motionless surface. They travel over a rotating globe, and this makes large-scale flows curve differently in the northern and southern hemispheres. This does not mean a tiny sink drain reliably spins one way because of Earth's rotation. That common claim is usually exaggerated because small local details dominate, but on planetary scales, the effect is real and powerful. It helps organize trade winds, storm systems, jet streams, and ocean circulation. The weather patterns that fill your forecasts are not only about heat and moisture, they are also about living on a turning planet. Rotation gives the atmosphere a kind of global choreography, bending motion into spirals, shaping storms into rotating structures, and helping distribute energy around the world. Even time itself in daily human life is built around Earth's rotation. Clocks, schedules, sleep cycles, workdays, prayers, meals, and artificial lighting all grew around the dependable return of the sun across the sky. Your body carries this rotation inward through circadian rhythms, biological timing systems that respond strongly to light and darkness. The planet turns, sunlight changes, hormones shift, alertness rises and falls, and what feels like your private daily rhythm is connected to a cosmic motion older than humanity. You are not just living on Earth, you are being timed by its spin. Yet Earth's rotation is not perfectly constant in the simple way a toy top might seem. It changes very slightly over time. Tides raised by the moon gradually slow Earth's rotation across vast periods, making days longer by tiny amounts. Large earthquakes, shifting masses of ice and water, and movements within Earth can also make minute changes in rotation. Scientists can measure these small variations with extraordinary precision, which is why modern timekeeping sometimes needs careful adjustment. The day feels absolute to you because your life is short, but the planet's rotation is a physical process, not a divine metronome fixed beyond change. It has a history, it has a future. Long ago, Earth spun faster and days were shorter. Far in the future, the relationship between Earth and Moon will continue evolving. This makes the ordinary word day feel less like a fixed container and more like a temporary agreement between a rotating planet, a star, and living beings who learn to organize their existence around the returning light. And perhaps the deepest lesson is not simply that Earth moves, but that your sense of motion is deeply local and deeply human. You can be carried at enormous speed and feel nothing if the motion is shared, smooth, and constant. You can mistake participation for stillness. You can build your whole sense of reality from what your body happens to notice. The ground feels stable not because it is motionless, but because its motion includes you. The sky feels like it turns because you turn beneath it. Morning feels like the world waking, but physically it is your side of the planet facing the sun again. So the next time you stand quietly under the open sky, remember that you are not standing on a static platform. You are on a rotating world, wrapped in an atmosphere rotating with you, turning eastward beneath the stars, carrying oceans into tides, winds into curves, cities into daylight, and sleeping bodies into morning. Stillness here is not a lie exactly. It is a local truth, a feeling made possible by shared motion. But beneath that feeling is a larger truth. The earth is moving you, even when you feel completely at rest. And every sunrise is the planet gently turning your life back toward the light. The moon pulls oceans constantly. The ocean is never simply lying still beneath the moon. It is being gently stretched by a force so steady that entire coastlines breathe with it. Stand beside the sea at night and the water may seem calm, almost sleepy, as if the surface is only responding to wind, waves, and weather. But even when the air is quiet, even when no storm is coming, the moon is pulling. Not just once, not only during dramatic full moons, not as a mystical command over water, but through gravity, constantly, patiently, across the whole planet. The moon pulls on Earth, on rock, on air, on your body, and on the oceans. But the oceans show the effect most visibly because they can move. The real secret of tides is not simply that the moon attracts water. If that were the whole story, you might expect one ocean bulge facing the moon and nothing more. But tides are born from difference. The side of Earth closer to the moon feels a slightly stronger lunar pull than Earth's center, while the far side feels a slightly weaker pull. That uneven pull stretches the planet's oceans into a long tidal shape, with one bulge generally facing toward the moon and another on the far side. The far side bulge is not there because the moon pushes water away. Gravity does not push like that. It appears because the Earth and ocean system is being pulled unevenly, and the far side water is left slightly less pulled toward the moon than the planet beneath it. This difference creates a stretching effect, a tidal force, and that force is what makes the ocean rise and fall. It is a subtle idea, but once you feel it, the whole sea changes meaning. The tide is not water being lifted by a giant hand. It is the ocean, responding to a planet-wide gradient in gravity, a difference across distance, a quiet imbalance written into space itself. As Earth turns beneath these tidal patterns, coastlines move through areas of higher and lower water, and the sea appears to advance and retreat. In many places, this creates 2 high tides and 2 low tides each lunar day. But the real ocean is not a perfect globe of water, so the pattern is never as simple as a classroom diagram. Continents block the flow. Ocean basins have shapes and depths that guide the water. Coastlines funnel, delay, amplify, or weaken tides. Islands split currents. Seafloor ridges redirect motion. In some regions, tides are small and almost invisible. In others, they become immense, rising and falling by many meters, because the shape of a bay or channel resonates with the tidal rhythm, like a room that makes certain sounds louder. The Bay of Fundy in Canada is famous for some of the highest tides on Earth, not because the moon pulls harder there, but because the local geography allows the tidal motion to build power. That is one of the most important lessons hidden in tides. A universal force meets local shape, and the result becomes place-specific. The same moon pulls on every ocean, but every coast answers in its own accent. The sun also participates. It is much farther away than the moon, but it is extremely massive, so its gravity creates tides too, though the moon's tidal effect on Earth's oceans is stronger. When the sun, Earth, and moon line up during new moon or full moon, lunar and solar tidal effects reinforce each other, producing stronger spring tides. The word spring here does not mean the season. It means the tide springs higher, When the moon is at a right angle to the sun from Earth's perspective, their tidal effects partly oppose each other, creating weaker neap tides. So the ocean is not only listening to the moon, it is responding to a changing gravitational conversation between Earth, moon, and sun. Every month, the height of the tide breathes through this cycle, rising more strongly, then calming, then rising again. And because the moon is orbiting Earth, tides do not arrive at exactly the same clock time each day. They tend to shift later, often by about 50 minutes, though local geography can complicate this. This means the tide is not simply a daily pulse. It is tied to the moon's motion, to a rhythm that slowly slides through the human clock. Fishermen, sailors, coastal communities, and marine animals have learned this rhythm not as theory, but as survival. Tide tables are not poetic decorations. They are practical maps of gravitational timing. They tell boats when harbors deepen, when mudflats appear, when currents strengthen, when rocks become hidden or revealed. Whole ecosystems live by this rising and falling edge. In tidal zones, creatures survive in a world that changes identity twice a day. A rock pool may be part of the ocean at dawn, and a tiny isolated universe by noon. Mussels, crabs, barnacles, seaweeds, worms, fish, and shorebirds all depend on the tide's schedule. The moon's pull becomes food access, shelter, danger, exposure, oxygen, moisture, and migration. What looks like water moving up and down is also a biological clock. The tide writes time into the shoreline. It creates one of Earth's most dynamic borders, where land and sea keep exchanging authority. Yet the ocean is not the only thing that rises. The solid Earth also experiences tides. Rock is much stiffer than water, but it is not perfectly rigid. The ground beneath you can deform slightly under lunar and solar tidal forces, rising and falling by small amounts that sensitive instruments can detect. The atmosphere has tides too, shaped by gravity and heating from the sun. This means the moon's pull is not just a story about beaches. It is a reminder that the whole planet is flexible in ways your body cannot feel. The Earth is not a dead stone under a distant lamp. It is a responsive body, subtly stretched by its companion in space. And over immense time, tides do more than move water. They create friction as oceans drag across basins and coastlines, converting some rotational energy into heat and slowly changing the Earth-Moon relationship. The Moon is gradually moving away from Earth by a few centimeters per year, measured with laser reflections from instruments left on the lunar surface. This does not matter for your next sunrise or your next beach walk, but it matters for the deep history of the planet. Long ago, the Moon was closer, tides were stronger, and Earth's days were shorter. The calm rhythm you know now is only one chapter in a much longer dance. The tide is not just motion in water, it is a record of gravitational partnership across billions of years. And perhaps this is why tides feel so strangely emotional when you watch them. The sea comes in, the sea goes out, and it seems like repetition. But it is not empty repetition. It is celestial mechanics made visible. It is the Moon touching Earth without contact. It is distance becoming movement. It is gravity turning into wet sand, exposed shells, lifted boats, rushing channels, and dark water climbing the rocks. You cannot see the force itself. You cannot hold gravity in your hand, but you can watch its consequences arrive at your feet. The tide teaches that not all motion begins nearby. Some of the most powerful changes in your world are caused by relationships across space. A body far above you can reshape the shore below you. A silent object in the sky can organize the habits of animals, the plans of sailors, the design of ports, and the rhythm of entire coastlines. And it does this not violently, not with thunder, not with obvious command, but with persistence. Pull after pull, day after day, the Moon reminds the ocean that it is connected to something beyond the horizon. So the next time you stand near the water and see the tide creeping inward, do not think of it as only the sea changing level. Think of it as Earth answering the Moon. Think of every wave arriving on top of a deeper planetary motion, every wet stone as evidence of an invisible force, every exposed shell as a timestamp written by gravity. The ocean is not still water waiting for weather. It is part of a cosmic system, constantly stretched, released, delayed, amplified, and shaped by the bodies around it. And maybe the quiet lesson is this: even when you feel alone on solid ground, the world beneath you is being moved by distant relationships. Nothing is completely separate. The moon pulls the oceans constantly, and the shore, without a word, rises to answer. Continents drift slowly. The ground beneath your feet feels like the definition of permanence, yet it is part of a slow migration that has been redrawing the planet for hundreds of millions of years. You stand on land and call it stable because it does not slide under you like ice, does not ripple like water, does not visibly travel across the horizon. A continent seems like the opposite of motion: heavy, ancient, rooted, almost eternal. But this confidence belongs to human time, not Earth time. The continents are moving, not as loose rafts drifting over an ocean, but as parts of enormous tectonic plates, rigid outer shells of Earth that creep across the planet's surface at speeds often measured in centimeters per year. That may sound too slow to matter until you realize that centimeters become kilometers when time is allowed to become geological. A fingernail grows too slowly for you to watch second by second, but over weeks it must be cut. In the same way, continents move too slowly for a human afternoon, but over millions of years they open oceans, close seas, split landmasses, rearrange climates, carry fossils across latitudes, and turn yesterday's coastline into tomorrow's mountain range or desert plain. This idea was once considered almost absurd. In the early 20th century, Alfred Wegener proposed that continents had once been joined and later drifted apart, partly because the shapes of coastlines seemed to fit like broken pieces of a larger world, and because matching fossils and rock formations appeared on continents now separated by oceans. South America and Africa looked as if they had once touched. Similar ancient organisms were found across distant lands, where they could not have easily crossed modern oceans. Rock layers and mountain belts lined up across continents as though someone had torn a single page and scattered the pieces. Wegener had evidence, but he lacked a convincing mechanism, and many scientists rejected his idea for decades. The Earth, to them, seemed too solid for such wandering. But later discoveries changed everything. The ocean floor was mapped in far greater detail, and scientists found long underwater mountain chains called mid-ocean ridges, where new oceanic crust forms as material rises and spreads outward. They also found symmetrical magnetic stripes on the seafloor, records of Earth's magnetic field reversals preserved in cooling rock like a barcode written into the ocean crust. These stripes showed that the seafloor was not ancient and fixed. It was being created, pushed apart, and recycled. Continental drift became part of a larger theory: plate tectonics. The continents are embedded in moving plates, and those plates interact at their boundaries. Some separate, allowing new crust to form between them. Some slide past each other, building tension that may eventually release as earthquakes. Some collide, compressing the crust. Some dive beneath others in subduction zones, carrying old oceanic crust back into the mantle. This is not a planet made of motionless stone. It is a planet with a moving skin. The mantle below the plates is not liquid in the way water is liquid, but over immense time it can flow like a very slow, hot, deformable solid. Heat from Earth's interior helps drive this deep motion, while gravity also plays a crucial role through processes such as slab pull, where dense oceanic plates sink into the mantle and help pull the rest of the plate along. There is no single giant motor dragging all continents in a simple direction. Plate motion is a system of forces: heating, cooling, sinking, spreading, resistance, and deep planetary structure. It is slow, but it is not weak. It is the reason the Atlantic Ocean has been widening. It is the reason India, once a separate landmass moving northward, eventually collided with Asia. It is the reason the map of the world today is only a temporary arrangement, a frame in a film that began long before humans and will continue long after us. If you could compress hundreds of millions of years into a few minutes, the continents would stop looking like fixed objects and begin to look alive with motion. They would merge into supercontinents and break apart again. Pangaea, the famous supercontinent, was only one chapter, not the first and not necessarily the last. Before it, other supercontinents existed. After us, new arrangements will form. The continents are not wandering randomly. They are following the physical behavior of plates, but from a human view, the result feels almost dreamlike. Africa inching, Australia racing northward by geological standards, the Americas shifting, oceans opening and closing like slow breaths in rock. And this movement is not only something reconstructed from ancient evidence. We can measure it today. Modern GPS stations fixed to bedrock can detect plate motion with astonishing precision, showing landmasses creeping year after year. The continent beneath you is not merely believed to move because of fossils or old rocks. It is measured moving now. That fact should disturb your sense of stillness in the best possible way. The map on a wall looks final because paper cannot show time. Borders look sharp because politics pretends the ground is permanent. But the earth beneath those borders is older, slower, and less obedient. Continents carry histories inside them. Traces of ancient seas, deserts, glaciers, volcanic arcs, vanished coastlines, and collisions so old that their violence has softened into hills and buried roots. A rock in one country may once have been near a completely different climate zone. A desert may preserve evidence of ancient ice. A fossil found far inland may belong to a time when that place was connected to a different shoreline, a different world, a different arrangement of continents under a different sky. Continental drift teaches that location is not destiny. It is a temporary address in a moving system. Even the idea of home becomes geologically strange. The land you call home has traveled through latitudes, climates, and eras. It may have been part of another continent, bordered another ocean, or sat closer to the equator in a past so distant no human memory can reach it. You inherit a place that has never truly stayed where it was. And yet, this motion is not chaos. It builds the conditions for life in deep ways. Plate tectonics helps recycle carbon through rock, volcanoes, oceans, and atmosphere over long timescales, influencing climate stability. It creates varied landscapes, ocean basins, shallow seas, island arcs, and nutrient cycles. It exposes fresh rock to weathering, helps regulate atmospheric gases across immense spans, and continually renews the surface of the planet. A completely frozen crust never moving might look peaceful, but it would also be a world without this deep recycling. Earth's slow restlessness is part of its habitability. The same movement that causes earthquakes and volcanic danger also helps make the planet dynamic enough to support complex environments. That is the uncomfortable balance of geology. The forces that threaten human structures are also part of the planetary system that shape the world we depend on. So when you look at a continent, do not imagine a dead slab of land resting forever in place. Imagine a passenger on a plate, a massive traveler moving so slowly that only fossils, satellites, seafloor stripes, and deep time can reveal the journey. Imagine coastlines as temporary edges, oceans as temporary openings, mountain belts as old conversations between moving plates, and maps as snapshots of a restless planet pretending, for one human lifetime, to be still. The lesson is quiet but enormous. Earth does not need speed to transform itself. It only needs time. And beneath every city, every forest, every border, every road, the continents continue their slow drift, carrying the surface of your world through a story much longer than your senses can hold. Mountains rise and erode. A mountain can look like the most finished thing on Earth, but it is really a slow argument between forces that lift it and forces that take it apart. You see a peak rising into the sky, and your mind calls it permanent, ancient, immovable, almost outside of time. Snow sits on its shoulders, clouds break against it, villages grow in its shadow. Roads bend around it as if the mountain were a final answer the world must obey. But every mountain is unfinished. Every ridge, cliff, valley, and summit is part of a process still happening, even when nothing seems to move. Mountains are born when Earth's crust is pushed, thickened, folded, broken, or lifted. Sometimes this happens where great pieces of crust collide and compress the land between them, forcing rock upward over immense spans of time. Sometimes mountains rise near zones of volcanic activity, where molten material builds cones, chains, and highlands. Sometimes large regions are uplifted by deep forces within Earth, raising plateaus that rivers later carve into dramatic relief. But rising is only half the story. The moment a mountain begins to climb, destruction begins too. Wind, rain, ice, rivers, gravity, chemical reactions, freezing water, plant roots, landslides, and glaciers all begin working on it. Not with hatred, not with purpose, just with persistence. The mountain grows, and the world begins reading it down. This is why mountains are not just monuments of uplift. They are records of erosion. Their shapes tell you what has been removed as much as what has been raised. A sharp peak may speak of glaciers cutting deeply into rock. A rounded hill may speak of long weathering and age. A steep canyon may reveal a river lowering its bed grain by grain, season by season, flood by flood. The visible mountain is only the current balance between building and wearing away. Underneath it, there may be a deep root of thickened crust extending downward. Because high mountains often float in a sense on denser material below, like icebergs with hidden mass beneath the waterline. When erosion strips material from the surface, the crust can respond by rising slightly, a process called isostatic rebound. This means that removing a mountain can sometimes help lift what remains. It is as if the earth, relieved of weight, slowly exhales upward. So a mountain is not a simple pile of rock. It is a living balance between deep support, surface attack, and gravitational adjustment. The forces that destroy it can also expose its hidden interior. Rocks once buried deep underground may appear at the surface after millions of years of erosion, carrying minerals and structures formed under heat and pressure far below your feet. When you hold such a stone, you may be touching a piece of ancient depth that only became visible because a mountain was slowly opened by time. This is one of geology's quiet miracles. Erosion does not merely erase, it reveals. It removes the cover from old worlds. It turns buried pressure into landscape. It carries the memory of high places down into rivers, plains, deltas, and oceans. Every grain of sand on a beach may be the afterlife of a mountain. It may have been broken from a cliff by frost, rolled through a stream, polished in a river, paused in a floodplain, buried, released, and carried again until it reached the sea. What you call a mountain and what you call a beach are not separate stories. They are different chapters of rock in motion. Rainwater seeps into cracks and reacts with minerals. Carbon dioxide dissolved in water forms weak acids that slowly alter certain rocks. Ice forms in fractures and expands, prying them wider. Rivers cut downward when land rises or when their energy increases. Glaciers, heavy and patient, grind and pluck bedrock, carving U-shaped valleys, cirques, and jagged arêtes. Landslides move whole sections of slope in moments, reminding you that slow change can sometimes release as sudden violence. The mountain seems calm from far away, but close up it is full of signals. Loose stones at the base of cliffs, fresh scars from rockfall, streams colored by sediment, slopes creeping downward, snowmelt feeding channels, roots entering cracks, lichens beginning chemical work on bare stone. Even temperature matters. A mountain expands and contracts slightly with heating and cooling, and over long periods those small stresses help weaken exposed rock. Nothing needs to happen dramatically for the mountain to be changing. A drop of water, a cold night, a gust of wind carrying grit, a root growing into a fracture, a river moving one pebble. These are small acts. But geology is the art of giving small acts enough time to become architecture. And mountains influence the world even as the world reshapes them. They steer winds upward, forcing air to cool and release moisture as rain or snow. One side of a mountain range may become wet and forested, while the other lies in a dry rain shadow. They store water as snow and ice, releasing it into rivers that feed valleys, farms, cities, and ecosystems far below. They create habitats stacked by elevation, where climate changes as you climb. They affect weather, water, biodiversity, and human settlement. A mountain is not just a high place. It is a machine of climate, water, erosion, and life. Yet it is also temporary. The Himalayas are still rising in places because the collision that built them continues. but they are also being eroded every day. The Appalachians, once far higher and more dramatic, have been worn down into older, softer forms. Ancient mountains can become low hills. Young mountains can be sharp and dangerous, but youth and age in geology are measured differently than in human life. A mountain range can be old beyond imagination and still not be finished. It can be rising and dying at the same time. That contradiction is not a flaw. It is the heart of the subject. Growth and erosion are not always separate phases. They can occur together, shaping each other. The faster a mountain rises, the more strongly rivers may cut into it. The more deeply valleys are carved, the more unstable slopes can become. The more material is removed, the more hidden rocks may rise and cool. The mountain is a conversation, not a sculpture. And perhaps this is why mountains feel sacred to so many cultures. They seem to connect earth and sky, but they also connect visible calm with invisible force. They remind you that height has a cost. To rise is to be exposed. To stand above the surrounding land is to invite weather, ice, gravity, and time to work on you. A mountain's greatness is not that it escapes erosion. It is that it becomes itself through erosion. Its beauty comes from what has been cut away. Its valleys are wounds that became pathways. Its cliffs are fractures turned into faces. Its summit is not a permanent throne, but a temporary edge in an ongoing transformation. So when you look at a mountain, do not see only a mass of stone resisting time. See a slow motion event, a place where the deep earth pushes upward and the surface world pulls downward, where clouds become rivers, rivers become sediment, sediment becomes future rock, and ancient pressure becomes a landscape you can stand before in silence. The mountain is rising, the mountain is eroding, the mountain is becoming and unbecoming at once. And maybe that is the quiet lesson it offers. Permanence is often just change moving too slowly for the heart to fear it. And even the strongest things are shaped not only by what lifts them, but by what patiently wears them away. The atmosphere is always flowing. The air around you looks invisible, but it is never truly resting. It is a moving ocean wrapped around the planet. You sit in a quiet room, and the atmosphere seems absent, as if air were only an empty allowance for breathing, a transparent gap between objects. But that quietness is only what your body can ignore. Around you, above you, and far beyond the clouds, the atmosphere is constantly shifting, rising, sinking, folding, cooling, warming, carrying moisture, spreading dust, lifting seeds, steering storms, and connecting distant parts of the world through motion. Air is not nothing. It is a fluid, just much thinner than water. And because it is a fluid, it flows whenever pressure, temperature, gravity, and terrain give it a reason to move. You do not always feel this flow, because some of it is slow, some of it is high above you, and some of it moves as part of systems too large for your skin to recognize. But step outside on a windy day and suddenly the invisible becomes physical. Air presses against your face. It pulls at your clothes. It moves leaves, bends grass, carries the smell of rain, and turns silence into sound. That moment is not air becoming active. It is you finally noticing what was already happening. The atmosphere is always searching for balance, but balance is constantly being disturbed. Sunlight warms the planet unevenly. Land heats and cools faster than water. Dark surfaces absorb more energy than bright ones. Mountains force air upward. Forests release moisture. Deserts bake. Oceans evaporate. Cities store heat. Polar regions lose energy into space. Because of these differences, air pressure changes from place to place, and air begins to move from regions of higher pressure toward regions of lower pressure. Wind, at its simplest, is the atmosphere trying to reduce imbalance, but the path is never perfectly simple. Air does not move across a still, flat world. It moves over a curved planet with oceans, continents, mountains, seasons, and spinning motion. It rubs against the ground near the surface. It is slowed by forests and buildings. It speeds through valleys. It piles up against slopes and spills over ridges. It rises when warmed, sinks when cooled, twists when forced around obstacles, and forms waves, eddies, and turbulence like water in a river. This is why wind is not just air going somewhere. It is a visible symptom of invisible differences. It is pressure becoming motion. It is heat becoming circulation. It is geography shaping breath. One of the great engines of atmospheric flow begins with rising air. When sunlight warms the ground warms the air above it. Warmer air usually becomes less dense than the surrounding air, so it tends to rise. As it rises, it expands because the pressure around it decreases, and expansion cools it. If that rising air contains enough water vapor, cooling can make the vapor condense into tiny droplets or ice crystals, forming clouds. This means a cloud is not simply a decoration in the sky. It is evidence that air has moved upward and changed state. It is motion made visible. Sometimes this upward motion is gentle, forming soft, fair weather clouds. Sometimes it becomes powerful, feeding towering storm clouds that reach high into the atmosphere. Inside those storms, air can rise rapidly, sink violently, rotate, freeze droplets, build hail, separate electrical charge, and release rain with sudden force. A storm is not an object floating above you. It is an atmospheric process, a living structure of flow. Even clear skies have motion. There are broad circulation patterns moving air through the tropics, mid-latitudes, and polar regions. There are fast rivers of air high above the surface called jet streams, which guide weather systems and influence the paths of storms. There are sea breezes that form because land and water warm differently during the day, drawing cooler marine air inland. At night, the pattern can reverse as land cools faster. There are mountain breezes, valley winds, monsoon circulations, trade winds, and seasonal shifts that have shaped agriculture, sailing, migration, architecture, and culture. Human history was written partly by atmospheric flow. Ships crossed oceans by learning dependable winds. Farmers learned the timing of rainy seasons. Cities rose near climates made livable by air and water patterns. Even today, airplanes ride or fight upper-level winds. Pollution travels across borders. Wildfire smoke can cross continents. And desert dust can fertilize distant ecosystems after being carried through the sky. The air above one place does not belong only to that place. Atmosphere is connection. What happens over an ocean can become weather over land. What rises from a forest can become moisture in a cloud. What burns in one region can become haze in another. The atmosphere makes the planet shared, whether we remember that or not. And yet for all this motion, the atmosphere is also layered. Near the ground, in the part of the atmosphere where weather mostly happens, air is dense enough to breathe and to carry the storms, clouds, and winds you know. Higher up, the air thins. Temperatures change in different ways, and motion follows different rules. Balloons, aircraft, satellites, and instruments have revealed that the sky is not a single simple space, but a structure with regions, boundaries, and transitions. You live at the bottom of this aerial ocean, where gravity holds most of the air close to Earth, and every breath you take comes from that compressed lower layer. Air pressure at sea level is not small. The atmosphere is pressing on you all the time with the weight of the air above. You do not collapse because pressure inside your body balances it, and because the force comes from all directions. Still, that invisible weight is real. It changes with altitude. It helps determine how gases move in and out of your lungs. It shapes boiling points, weather patterns, and the way your body responds in high mountains. The air is light in your hand, but enormous when stacked to the edge of space. This is one of the atmosphere's quiet paradoxes. It is delicate enough to move with a warm surface, yet massive enough to shape oceans, landscapes, and life. It can be calm enough to let a feather drift, and violent enough to tear roofs from houses. It can carry a scent across a garden, or carry a hurricane across a sea. It can cool your skin, feed a fire, scatter seeds, lift birds, turn turbines, and carve dunes. It is invisible only because your eyes are not made to see it directly. But every flag, every cloud, every drifting leaf, every changing pressure reading, every bend of smoke, every distant storm line is the atmosphere showing its hand. And maybe the deeper lesson is that stillness in the air is often just motion too balanced to feel. A room may seem quiet, but warm air rises from your body. Cooler air slips downward. tiny currents form near walls and windows, and ventilation slowly exchanges one pocket of air for another. Outside, even on a calm day, the atmosphere is flowing on scales larger than your senses can hold. Above you, winds may be racing while the ground feels still. Far away, pressure systems may be forming that will become tomorrow's weather. The sky is not an empty roof. It is a moving system that you live inside. So the next time you look up and see nothing but blue, remember that the blue is not a ceiling over a motionless world. It is the color of light scattered through a restless atmosphere. Remember that air is always moving, even when it arrives softly, even when it seems to wait, even when you forget it is there. The atmosphere is Earth's invisible circulation, a flowing skin around the planet, carrying heat, water, life, danger, and change. And every breeze that touches you is only the smallest local whisper of a much larger motion, a reminder that you are not breathing inside emptiness, but inside a planet-wide river of air. Oceans move heat around Earth. The ocean is Earth's slow-moving memory of sunlight, storing warmth in one place and carrying it quietly toward another. When you look at the sea, it may appear like a surface. Waves, reflections, foam, a horizon line that seems to separate water from sky. But beneath that surface is one of the planet's greatest heat-moving systems, a vast circulating body that absorbs energy, hides it, releases it, and redistributes it across distances so large that no human sense can easily follow them. Water has an unusual ability to hold heat without changing temperature quickly. A beach can become scorching under the afternoon sun while the sea beside it remains comparatively cool. Not because the ocean is untouched by sunlight, but because water takes in a great deal of energy before its temperature rises much. This high heat capacity makes the ocean act like a planetary buffer. It softens extremes, it slows sudden changes, it absorbs warmth during hotter periods and gives it back more gradually when the air cools. That is one reason coastal places often have milder climates than inland regions. The sea is not just scenery beside the land. It is a thermal reservoir, a deep blue bank account of energy, receiving sunlight day after day and spending it slowly through currents, evaporation, storms, and contact with the air above it. But the ocean does not store heat evenly. Sunlight warms the tropics much more strongly than the poles, and this creates a planetary imbalance. Near the equator, the ocean receives intense energy. In colder regions, it loses more heat to the atmosphere and to space. If nothing moved, the tropics would become far hotter and the poles far colder. But the ocean moves. Surface currents carry warm water away from low latitudes, while colder water returns through other pathways. This circulation is not a single river with clean banks. It is a layered, changing, global pattern shaped by winds, Earth's rotation, water density, coastline geometry, seafloor depth, temperature, and salt. Some currents are near the surface, pushed strongly by winds and guided by continents. Others move deep below, driven by differences in density. Warm water is usually less dense than cold water, and fresher water is less dense than saltier water. When seawater becomes cold and salty enough, especially in certain high-latitude regions, it can sink into the deep ocean and begin a long journey through the planet's interior waters. This is part of what scientists often call the global overturning circulation, a slow exchange between surface and depth that can carry heat, salt, carbon, oxygen, and nutrients around the world. It does not move with the speed of a storm. Some deep waters may travel for centuries before returning to the surface. The ocean has patience beyond human imagination. A drop of water can enter the dark deep, move through basins, pass beneath ships and storms without being seen, and rise again long after the human world above it has changed. In that sense, the ocean is not only moving heat through space, it is moving heat through time. One of the most famous examples of ocean heat transport is the system of currents in the Atlantic that helps carry warm water northward. Warm surface water flowing toward Europe releases heat into the air, influencing regional climate, while colder, denser water can sink in northern regions and contribute to the deeper circulation. This does not mean the ocean is a simple heater aimed at one continent, and it does not mean any one current explains an entire climate by itself. Weather and climate are built from many interacting parts, but ocean currents are major players. They help decide where warmth is delivered, where moisture becomes available, where sea ice can form, where storms gain energy, and where marine life finds nutrients. The water that seems flat from a distance is part of a planetary distribution system. It is carrying the energy of sunlight through paths no road can show. At the surface, winds drag water into motion, but the moving water does not simply follow the wind in a straight line. Because Earth rotates, broad currents are bent and organized into great circular systems called gyres. These gyres move warm water, cool water, floating material, and biological life across entire ocean basins. Western boundary currents like the Gulf Stream and Kuroshio can be especially strong, narrow, and warm, carrying tropical heat poleward with remarkable power. On the other side of ocean basins, slower, broader currents return cooler water toward lower latitudes. This enormous looping motion helps connect climates that seem separate. A change in one part of the ocean can echo elsewhere through currents, temperature patterns, and atmospheric responses. The ocean is not a local body of water. It is a connected system with distant consequences, and sometimes the ocean reveals this connection dramatically. During El Niño events, unusually warm surface water spreads across parts of the tropical Pacific, changing patterns of rainfall, drought, storm tracks, and marine ecosystems across the globe. A shift in ocean heat thousands of kilometers away can affect crops, fisheries, floods, wildfires, and winters in places that never see the tropical Pacific. That is the hidden reach of ocean heat. It does not stay where it enters. It travels through currents, through evaporation, through cloud formation, through pressure patterns, through the living machinery of climate. The sea is not passive under the sky. It is one of the sky's deepest sources of change. Evaporation is another way the ocean moves heat. When water evaporates from the surface, it carries energy with it in a hidden form called latent heat. The vapor rises into the air, travels with winds, and later releases that energy when it condenses into clouds and rain. This is one reason tropical storms and hurricanes can become so powerful over warm ocean water. They draw energy from the warm surface through evaporation and condensation, turning stored ocean heat into towering cloud systems, fierce winds, and heavy rainfall. The storm is not powered by water alone, but by the energy exchange between warm ocean and atmosphere. In a calmer form, the same process feeds ordinary rain systems and the water cycle. The ocean warms, water evaporates, air carries moisture, clouds form, rain falls, rivers return water to the sea, and the loop continues. Heat is moving inside that loop, disguised as vapor, clouds, and rainfall. The sea is constantly translating sunlight into motion. Beneath the surface, heat also shapes life. Warm and cold layers can remain separated because warm water tends to stay above colder, denser water. This layering, called stratification, can limit the mixing of nutrients from deeper waters into sunlit surface layers. In other places, upwelling brings cold, nutrient-rich water upward, feeding plankton, fish, seabirds, and entire marine food webs. Some of the richest fisheries on Earth depend on this upward movement. So ocean heat is not just a climate detail. It affects where life blooms and where it struggles. A change in temperature can alter oxygen levels, coral health, species migration, breeding patterns, and the timing of biological events. Coral reefs, for example, can bleach when water stays too warm for too long, because the delicate relationship between corals and their symbiotic algae breaks down under stress. The ocean's heat is therefore not abstract. It is written into living color, into migrations, into fisheries, into the survival of ecosystems. And because the ocean absorbs and redistributes so much energy, it also hides change from immediate view. The air may warm quickly, but the ocean can take in heat slowly and store it below the surface, delaying the full expression of change. This does not make the heat disappear. It means the ocean is carrying a delayed story. Some of that stored energy can later influence weather patterns, ice melt, sea level rise through thermal expansion, and long-term climate behavior. Warm water expands slightly, and when enormous volumes of ocean warm, even small expansion matters. Again, the ocean teaches scale. A tiny change spread across a vast body becomes a planetary effect. A small temperature shift in human terms can be enormous when it involves the upper layers of entire seas. This is why the ocean can seem calm while holding profound change within it. Its surface may glitter peacefully, yet below that beauty is a thermal history of seasons, currents, storms, and human influence. The sea remembers what the air forgets. It stores energy beyond the length of a day, beyond a season, sometimes beyond a lifetime. So when you stand by the ocean, do not see only waves arriving at shore. See a moving climate engine. See sunlight stored in water. See warm currents traveling like invisible roads. See cold, deep water carrying old signals through darkness. See evaporation lifting heat into clouds. See nutrients rising where the sea turns over. See storms feeding from warmth. Coastlines softened by marine air. Polar waters sinking into long journeys. And distant regions connected by a circulation too large to fit inside ordinary thought. The ocean moves heat around Earth not with haste, but with immense patience. It is the planet's slow circulatory system, a blue pulse that makes climates gentler, weather possible, ecosystems alive, and distance less separate than it seems. And perhaps the quiet lesson is this: what looks like a boundary at the shore is really a connection. The water touching your feet may be part of a journey that began under another sky, carrying heat from another latitude, shaped by winds you never felt and depths you will never see. The ocean does not merely cover the earth. Clouds form and dissolve. A cloud is not a thing placed in the sky. It is a temporary agreement between invisible vapor, cooling air, tiny particles, and the patience of light. You look up and see a white shape drifting above you, soft enough to seem weightless, familiar enough to feel almost decorative. A cloud appears like a floating object, as if the sky has grown cotton, as if water has forgotten gravity for a while. But a cloud is not cotton, not smoke, not pure water vapor made visible. Water vapor itself is invisible. The cloud you see is made of countless tiny liquid droplets, ice crystals, or both, suspended in air because they are small enough to fall very slowly, and because the air around them is often moving upward or swirling enough to keep them aloft for a time. That simple correction changes everything. A cloud is not water escaping physics. It is water obeying physics at a scale your eyes cannot separate. The story usually begins with air that contains water vapor, gathered through evaporation from oceans, lakes, soil, leaves, and every wet surface under the sun. Warm air can hold more water vapor than cold air, not because the air is a container in a simple bucket-like way, but because temperature influences how much vapor can remain mixed in the air before condensation begins. When moist air rises, it enters regions of lower pressure, expands, and cools. If it cools enough, it reaches a point where it can no longer keep all that water in vapor form. The excess begins to condense into droplets, but not usually an empty space by itself. Water molecules need surfaces to gather on, and the atmosphere is filled with tiny floating particles that act as condensation nuclei. Sea salt, dust, smoke, pollen, pollution, volcanic ash, and microscopic fragments carried from land and sea. Without these tiny seeds, cloud droplets would have a much harder time forming in ordinary atmospheric conditions. This means every cloud has a hidden skeleton of dust and salt, and fragments of the world below. The sky is not separate from Earth. It lifts small pieces of the surface, wraps them in water, and turns them into brightness. That brightness comes from the way cloud droplets scatter sunlight. A single droplet is tiny, but a cloud contains so many droplets that light bounces and scatters in many directions, making the cloud look white or grey. Thin clouds may let much light through and appear glowing. Thick clouds block and scatter so much light that their bases become darker, not because they are dirty, but because less sunlight makes it through to the underside. This is why a storm cloud can look heavy and almost bruised, while a small fair-weather cloud shines like a soft white island. Its color is not a simple color painted onto it. It is the visible result of light struggling through a crowd of droplets and crystals. Clouds form in different ways because air is lifted in different ways. Sometimes the ground warms under sunlight, heating the air above it until it rises in columns, creating puffy cumulus clouds that build upward, like thoughts becoming visible. Sometimes air is forced up a mountain slope, cools, and forms clouds along ridges, as if the land itself is squeezing moisture from the sky. Sometimes warm air glides over colder air along weather fronts, spreading broad layered clouds across huge regions. Sometimes air converges and rises in deep tropical systems, feeding towering thunderheads that can grow into vast vertical structures, with warm droplets below, ice crystals above, and violent electrical processes inside. But even the calmest cloud is not frozen in identity. It is forming and dissolving at the same time. Droplets appear where air cools and becomes saturated. Droplets evaporate where drier air mixes in, or where the cloud edge warms. The border of a cloud is not a wall, it is a negotiation. At the edge, cloudy air meets surrounding air, and if the surrounding air is drier, some droplets shrink back into invisible vapor. This is why clouds can have ragged edges, why they fray, fade, rebuild, and vanish without ever falling as rain. A cloud is a process you mistake for an object because your eyes catch it in one moment. It is more like a flame than a stone, a shape maintained by continuous exchange. The water inside it may be constantly changing, yet the form remains for a while because the conditions keep rebuilding it. And clouds do not always produce rain because most cloud droplets are far too small to fall efficiently. They drift and collide, but many collisions simply bounce or merge only slowly. For rain to form in warm clouds, droplets must grow large enough through collision and coalescence, where bigger droplets collect smaller ones as they fall. In colder clouds, ice crystals can grow at the expense of supercooled water droplets, because the physics of vapor favors ice growth under certain conditions. Those crystals may become snowflakes, pellets, or melt into raindrops on the way down if the air below is warm enough. Precipitation is not cloud water simply deciding to fall. It is cloud particles growing past a threshold where gravity finally wins more clearly than suspension and upward motion. Until then, a cloud may contain enormous total water spread across such tiny droplets that the whole structure remains suspended like a pale thought. This is also why a cloud can look massive and still contain surprisingly little liquid water compared with what its size suggests. The water is distributed through a huge volume of air. A large cloud may weigh a great deal in total, but that weight is spread out among countless microscopic droplets and supported by the moving atmosphere. It is not a giant bag of water hanging overhead. It is a dispersed field of droplets inside flowing air, and the moment the conditions change, the cloud changes. Sunlight can warm it, dry air can eat into it, rising motion can feed it, sinking air can compress and warm it, making droplets evaporate. Wind shear can stretch it into streaks. Turbulence can tear its edges. Night can cool the land and help low clouds or fog form near the surface. Morning sunlight can dissolve them again. Fog, in fact, is essentially a cloud at ground level. Proof that the difference between sky and surface is sometimes only altitude. When you walk through fog, you are inside what you normally look up at. Tiny droplets touch your skin, bead on your hair, soften sound, and erase distance. The cloud is no longer an object above you. It becomes an environment around you. This is one of the most beautiful reversals in weather. The sky can descend until you are walking through its unfinished thoughts. Clouds also help regulate Earth's temperature in complicated ways. Some reflect sunlight back to space, cooling the surface below. Others trap infrared radiation, helping keep warmth near the planet, especially at night. Their effect depends on their height, thickness, composition, timing, and location. Low bright clouds often reflect a lot of sunlight. High thin clouds may allow sunlight in while slowing the escape of heat. This makes clouds one of the more difficult parts of climate science, because they are shaped by tiny droplet physics and vast atmospheric circulation at the same time. A cloud can be born from a microscopic particle and still affect the energy balance of a continent. It can last minutes or organize into systems that cover thousands of kilometers. It can shade a field, feed a river, reflect sunlight, release latent heat, mark the path of rising air, or signal the arrival of a storm. Clouds are not passive decorations. They are visible chapters of the water cycle, atmospheric motion, and energy exchange. And perhaps their deepest lesson is that form does not require permanence. A cloud has an identity only while conditions maintain it. Change the temperature, moisture, pressure, wind, or surrounding air, and that identity fades. This is why watching clouds can feel strangely emotional. They seem to become something, hold themselves for a while, and then loosen back into invisibility. They remind you that not everything real is solid. Not everything meaningful lasts. Some things exist as balance, as timing, as a meeting between forces. The cloud was never a fixed object, yet it shaped the light, cooled the ground, carried water, and changed the sky. Its disappearance does not mean it was false. It means its conditions moved on. So the next time you see a cloud forming above you, do not see only a white patch in the blue. See air rising, cooling, reaching saturation. See invisible vapor becoming visible on dust and salt. See sunlight scattered by droplets too small to separate. See edges forming and dissolving as dry air eats into them. See a temporary body made from motion, temperature, water, and light. And when the cloud fades, remember that it has not simply died. Its droplets have returned to vapor, its water has rejoined the air, its particles may drift onward, and the same moisture may become another cloud under another sky. A cloud is the atmosphere thinking out loud for a moment and then becoming silent again. The sun vibrates like a bell. The sun is not silently burning above you. It is ringing with hidden vibrations that scientists can read like music from a star. From Earth, the sun looks smooth, distant, and almost steady. A bright disk that rises, crosses the sky, and disappears with the calm authority of something ancient and unshakable. But that calm face is an illusion created by distance. Up close, the sun is not a quiet golden ball. It is a vast sphere of plasma, a charged electrically active gas so hot that atoms are stripped apart into nuclei and electrons, moving under gravity, magnetism, pressure, and heat. Its surface is not solid. It has no hard crust, no glowing shell you could stand on, no fixed boundary like the skin of a planet. What we call the visible surface is really the layer from which most visible light escapes into space. And even that layer is alive with motion. Huge cells of hot plasma rise, cool, sink, and turn over, creating a grainy texture called granulation, as if the sun's surface were covered in millions of bright, restless cells. These motions do more than stir light. They shake the sun. They generate pressure waves, sound-like waves that travel through the solar interior, bounce, interfere, and resonate. In space, you would not hear the sun in the ordinary way, because sound needs material to travel through, and the vacuum between worlds cannot carry it to your ear. But inside the sun itself, where plasma is dense enough, pressure waves can move. The sun has an interior voice, not a voice made for human hearing, but a pattern of vibrations written into its surface. It is not one simple note. It is an enormous choir of oscillations, many overlapping modes, each carrying information about the layers it has traveled through. Some waves dive deep into the solar interior before turning back toward the surface. Others remain closer to the outer layers. Some travel across broad regions. Others are trapped in smaller patterns. Together, they make the sun behave less like a burning lamp and more like a resonating instrument, a star-sized bell whose ringing is too slow, too vast, and too complex for your ears, but not for science. The field that studies these vibrations is called helioseismology, and it works on a beautifully simple principle. If the inside of an object affects the waves moving through it, then studying those waves can reveal the hidden interior. On Earth, seismologists study earthquakes to learn about the inside of our planet. The waves pass through rock, bend, reflect, speed up, slow down, and carry clues about layers no one can directly visit. Helioseismology does something similar with the Sun, but instead of earthquakes, it uses solar oscillations. Scientists watch tiny movements on the Sun's surface, often through shifts in light that reveal motion toward or away from us. These surface motions are small compared with the size of the Sun, but they are measurable. One of the most important patterns is often called the 5-minute oscillation, because many of the Sun's visible surface vibrations repeat on timescales of several minutes. To the human eye, the Sun looks constant. To sensitive instruments, it is breathing in patterns of light and motion. The surface rises and falls, not as one simple sphere inflating and deflating, but in countless patches and waves. Every flicker in that pattern is a clue. By analyzing these oscillations, scientists have learned about the Sun's internal rotation, its temperature structure, the speed of sound inside it, and the behavior of plasma beneath the visible surface. This is astonishing when you pause to feel it. We cannot cut the Sun open, we cannot send a probe into its core and return with a sample. We cannot lower a camera through its burning layers, and yet by watching the way it vibrates, we can infer what is happening inside. The Sun reveals its hidden body through rhythm. Its vibrations become a kind of remote touch. They allow us to learn about depths that light itself cannot easily show us, because the light produced near the core takes a very long and complicated journey outward, scattering through the dense interior before finally escaping from the outer layers. The waves, however, carry another kind of information. They are shaped by the conditions inside the Sun, and when they appear at the surface, they bring the fingerprint of those conditions with them. This is one of the most elegant acts in modern astronomy, reading the inside of a star by listening to its surface tremble. These vibrations also teach that the Sun is not a simple furnace. It is a layered, dynamic system. In its core, nuclear fusion converts hydrogen into helium, releasing the energy that eventually becomes sunlight. Around that core, energy moves outward through regions with different behavior. In one deep zone, energy is transported mainly by radiation, passed from particle to particle in a long, indirect journey. Closer to the surface, convection becomes important, with hot plasma rising and cooler plasma sinking, like an enormous and restless circulation. These convective motions help excite the pressure waves that ring through the star. The Sun's magnetism complicates the picture further. Magnetic fields rise, twist, and concentrate, forming sunspots, active regions, flares, and coronal mass ejections. These magnetic features can interact with waves and flows, changing the local vibration patterns. This gives scientists a way to study not only the deep interior, but also the hidden structures beneath sunspots and active regions. A dark sunspot is not merely a stain on the solar face. It is a magnetic wound in the plasma, a place where strong magnetic fields suppress some of the usual convective motion and alter the way energy reaches the surface. Beneath and around such regions, the Sun's vibration patterns can change, offering clues about invisible magnetic architecture. The Sun, then, is not just ringing randomly. Its ringing is shaped by structure, motion, magnetism, and depth. It is a living instrument of plasma physics. And yet the metaphor of a bell must be handled carefully. A bell has a hard body. The Sun does not. A bell rings because metal vibrates after being struck. The Sun vibrates because turbulent motion, pressure, gravity, and plasma behavior continually excite waves inside it. A bell's sound travels through air to your ear. The Sun's acoustic waves remain inside the solar material, and what reaches us is light carrying the evidence of surface motion. The metaphor is useful because both systems resonate, but the Sun is stranger than any bell humans have ever built. It is an instrument with no solid walls, powered by nuclear fusion, shaped by gravity, and filled with plasma. Its notes are not played for an audience. They are the natural consequence of a star maintaining itself against collapse, transporting energy outward, and constantly adjusting its inner pressure. In that sense, the Sun's vibration is not decoration. It is part of its physical life. A perfectly still Sun would not be the Sun we know. Its apparent steadiness depends on continuous motion, balance, and feedback. Gravity pulls inward. Pressure pushes outward. Energy rises. Plasma circulates. Magnetic fields emerge and tangle. Waves travel through the interior. The star is stable on human timescales, not because nothing is happening, but because so much is happening in a balanced way. This is the same deeper lesson, but on a scale that almost overwhelms the mind. Stability is not always the absence of activity. Sometimes stability is activity arranged into endurance. The sun shines steadily because it is in dynamic balance, and its vibrations are one visible signature of that balance. They also connect you to the sun more intimately than the simple word sunlight can express. Every day, light from this vibrating star falls on your skin, warms the ground, powers weather, feeds plants, drives photosynthesis, and supports nearly every food chain you depend on. You live under a star that is not merely glowing, but pulsing with internal information. The warmth on your face comes from an object that scientists can study like a musical instrument, a star whose invisible pressure waves have helped reveal its hidden layers. When you look at sunlight on a wall, you are seeing the surface expression of a deep machine that has been ringing for billions of years. And perhaps that is why the idea feels quietly humbling. The sun seems obvious because it is always there, too bright to stare at, too familiar to question. But familiarity can make miracles disappear. We forget that this bright disk is a real physical body, larger than imagination, constantly transforming matter into energy, constantly vibrating, constantly sending both light and information into space. So the next time you feel the sun on your face, do not imagine a silent lamp hanging above the world. Imagine a star resonating in its own plasma, its surface trembling in patterns too subtle for your eyes, its interior revealing itself through waves that scientists patiently decode. Imagine a bell made not of metal, but of fire and gravity, ringing without sound across the language of light. And then ask yourself how many other things in your life seem silent only because you have not learned how to listen. Stars orbit galactic centers. The stars look pinned to the night, as if the galaxy were a frozen painting, but every one of them is traveling through an enormous gravitational dance. When you look up at the Milky Way from a dark place, the band of pale light can seem like a still river poured across the sky, a quiet haze of distant suns suspended in place. But that stillness is only the blindness of human time. Stars are not fixed decorations on a cosmic ceiling. They are moving bodies, each following a path shaped by the gravity of everything around it. Other stars, gas clouds, dark matter, stellar remnants, and the dense central regions of the galaxy. The sun itself is not sitting still at the edge of creation. It orbits the center of the Milky Way at tremendous speed, taking roughly hundreds of millions of years to complete one full circuit. That means the last time the sun was in a similar position around the galaxy, Earth was a completely different world, populated by different life, under different skies, with continents arranged differently and no human mind here to name the stars. A human lifetime is too brief to notice this journey directly, so the sky feels fixed. But on galactic time, your entire solar system is moving like a spark carried around a vast wheel. And the wheel is not simple. Many people imagine stars orbiting the center of a galaxy the way planets orbit the sun, as if everything circles one central object. But that picture is misleading. Yes, at the heart of the Milky Way sits a supermassive black hole called Sagittarius A, containing millions of times the mass of the sun. Close to it, stars can whip around in tight, fast orbits, and astronomers have watched some of those stars move over the years, using their paths to confirm the black hole's presence. But the black hole is not massive enough to control the whole galaxy by itself in the way the sun dominates the solar system. Most stars in the Milky Way are not orbiting the central black hole alone. They are orbiting the combined gravitational pull of the galaxy's mass. The stars in the bulge and disk, the gas, the dust, and especially the extended halo of dark matter that appears to surround the galaxy. This is a crucial distinction. A galaxy is not a solar system scaled upward. It is a self-gravitating city of hundreds of billions of stars, where the movement of each star is shaped by the mass distribution of the whole. The center matters, but so does everything spread around it. In the Milky Way's disk, Many stars follow broad paths around the galactic center, but they do not all move like beads on perfect circular rails. Their orbits can be slightly oval, tilted, wavy, and disturbed by encounters with spiral arms, giant molecular clouds, and the gravitational influence of neighboring structures. The disk itself rotates differentially, meaning stars at different distances from the center do not all share the same angular pace like points on a solid spinning wheel. The galaxy is not a rigid object. It is a flowing structure. Stars near different regions follow different orbital rhythms, and over time, those rhythms stretch, mix, and rearrange patterns. This is one reason spiral arms are often misunderstood. The spiral arms of a galaxy are not necessarily the same stars locked permanently into bright curved lanes. They can behave more like density patterns, regions where stars, gas, and star formation become more concentrated, while individual stars may pass through them over long spans. A spiral arm is not a painted stripe on a solid disk. It is a moving pattern in a gravitational system, like a traffic jam that persists even as individual cars enter and leave it. When gas clouds pass through these denser regions, they can be compressed, triggering the birth of new stars. The brightest, most massive young stars shine strongly but live relatively short lives, so they often highlight the spiral arms where they formed. This makes the arms look permanent and bright, while the actual stellar population is far more complex. A galaxy is not just rotating, it is organizing, dissolving, reforming, and carrying generations of stars through changing gravitational landscapes. Beyond the disk, stars can behave in even stranger ways. Some stars belong to the halo, moving on long, tilted, stretched-out orbits that may carry them far above or below the flat disk. Some may be ancient remnants of smaller galaxies that the Milky Way absorbed long ago. Others form streams, long trails of stars pulled out by gravity as dwarf galaxies or star clusters are torn apart. These stellar streams are like fossils of galactic history, not buried in rock, but stretched through space. They reveal that galaxies grow by eating smaller systems, merging, disturbing, and inheriting stars that were born elsewhere. The stars you see are not only orbiting, some are carrying memories of vanished galaxies inside their motions. In elliptical galaxies, where the shape is more rounded or stretched rather than a flat spiral disk, stellar motion can be even less like orderly circling, and more like a swarm of paths in different directions. The word orbit still applies, but the image of neat rings fails. Gravity can hold a system together without arranging everything into a calm wheel. Order in the universe does not always look like symmetry from the outside. Sometimes it looks like billions of paths woven into one stable whole. And this is where dark matter enters the story honestly, not as a fantasy, but as a necessary clue from observation. When astronomers measure how fast stars and gas orbit in galaxies, they find that the visible matter alone does not explain the motion. In many spiral galaxies, stars far from the center move faster than expected, if only the visible stars and gas were providing gravity. This suggests that galaxies are embedded in much larger halos of unseen mass, dark matter. We do not yet know what dark matter is made of, but its gravitational effects are central to how galaxies rotate and hold together. Without it, the outer parts of galaxies would not move as they do under our current understanding of gravity. So when a star orbits a galactic center, it is not just responding to the glowing matter we can photograph. It is also responding to an invisible gravitational architecture. The galaxy you see is only the luminous part of a larger structure. The night sky shows you the lights, but not the full building. The motion of stars reveals the missing walls. This is one of the most powerful lessons in astronomy. Movement can expose what light cannot. A star's path becomes evidence. Its speed becomes testimony. Its orbit becomes a way of weighing the unseen. And thanks to modern sky surveys and space telescopes, scientists can measure stellar motions with extraordinary care. The European Gaia mission, for example, has mapped positions and motions for vast numbers of stars in the Milky Way, turning the galaxy from a flat-looking band in the sky into a dynamic system we can study in 3 dimensions. With enough measurements, astronomers can trace streams, discover past mergers, refine the shape of the galaxy, and understand how stars travel through the disk and halo. The galaxy is no longer merely something we photograph, it is something we can watch in motion, even if that motion must be reconstructed from tiny shifts across years and decades. And perhaps the most humbling part is that you are inside the thing you are trying to understand. You cannot step outside the Milky Way and see it whole with your own eyes. You study it from within, like a person inside a cathedral, trying to understand the entire building by measuring echoes, shadows, and the motion of dust in beams of light. Every star you see is both a point of beauty and a moving data point in a gravitational system. Every constellation is temporary, not because the stars vanish quickly, but because their motions slowly change the apparent patterns. Given enough time, the familiar shapes humans have drawn in the sky will deform and disappear. Orion will not always look like Orion. The Big Dipper will not always keep its form. The stories written in the stars are not eternal carvings. They are human meanings placed on moving lights. This does not make them less beautiful. It makes them more fragile, more alive, more connected to time. So when you look at the night sky and feel peace, remember that peace is not the absence of motion. It is motion too large and too slow for your senses to follow. Above you, stars are orbiting the galactic center, dipping through the disk, passing near clouds, joining streams, escaping clusters, and carrying the chemical history of older generations. Your own sun is moving with them, pulling Earth and every human life along a path around the Milky Way's hidden center. You are not standing beneath a fixed sky. You are riding a star that is riding a galaxy. And the galaxy itself is not a still island, but a rotating, evolving, dark matter-laced system of light and gravity. Maybe that is the quiet truth the stars offer when you stop seeing them as decorations. Nothing in the sky is merely waiting. Everything is on a journey. Even the lights that taught us the meaning of stillness. The Milky Way moves through space. Your galaxy is not a quiet island in space. It is a vast moving vessel being carried through a universe with no fixed shore. When you imagine the Milky Way, you may picture a grand spiral suspended in darkness, beautiful and still, like a luminous whirlpool frozen inside an endless black sea. But that image is only a human simplification. The Milky Way is not hanging motionless in the cosmos. It is moving, pulled and guided by gravity, traveling with other galaxies, falling towards some structures, receding from others, and participating in motions so large that even the word speed begins to feel too small. The strange part is that there is no absolute background in space that lets you say, in the simplest possible way, this is standing still. Motion in the universe is usually measured relative to something else. Nearby galaxies, galaxy clusters, the expanding fabric of space, or the faint afterglow of the early universe called the cosmic microwave background. Against that ancient radiation, our cosmic neighborhood is moving at hundreds of kilometers per second. That means the Milky Way, the Sun, Earth, your body, and every quiet object around you are part of a motion that never appears in your senses. You do not feel the galaxy move because you are inside the moving system, and because space offers no wind against your face, no cosmic road beneath your feet, no external marker rushing past your window. A galaxy can cross the universe with immense speed and still feel like home to the beings inside it, but the motion is real. We know it partly because the cosmic microwave background is not perfectly the same in every direction from our point of view. One side of the sky appears very slightly warmer and the opposite side very slightly cooler, a pattern caused mainly by our motion through that ancient field of radiation. It is as if the universe left behind a faint thermal wallpaper from its early fire, and by studying the tiny shift in that wallpaper, we can tell that our cosmic home is moving. This is one of the most beautiful kinds of evidence in astronomy. Not a roaring engine, not a visible trail, not a streak behind the galaxy, but a whisper in the oldest light we can observe. The Milky Way belongs to a small family of galaxies called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and many smaller dwarf galaxies. These galaxies are gravitationally bound to one another, meaning their mutual gravity is strong enough to matter more than the general expansion of the universe across that local region. This is why Andromeda is not being carried away from us by cosmic expansion. It is actually approaching the Milky Way, and in several billion years the two galaxies are expected to merge into a larger system. That future collision will not look like two solid objects smashing in the way cars collide. Galaxies are mostly empty space, so individual stars are unlikely to crash directly into one another. Instead, the galaxies will pass through and distort each other gravitationally, stretching streams of stars, triggering new star formation in gas-rich regions, reshaping orbits, and eventually settling into a new structure. The word collision makes it sound sudden and violent in a human way, but galactic merging is a slow transformation, a dance of gravity lasting hundreds of millions to billions of years. The Milky Way is therefore not merely moving alone. It is moving as part of a group, and that group is moving within a larger cosmic neighborhood. Nearby lies the Virgo cluster, a much larger gathering of galaxies, and beyond that, the broader cosmic web, a structure of filaments, walls, clusters, and enormous voids. Galaxies are not sprinkled randomly through space like glitter. They form patterns, drawn together along invisible gravitational architecture, dominated in large part by dark matter. The Milky Way's motion is influenced by this wider distribution of mass. Astronomers speak of flows toward massive regions, including structures historically associated with the Great Attractor, and of an even larger region called Laniakea, a proposed supercluster-scale home for our galaxy and many others. These names can sound mythical, almost too dramatic, but they are attempts to map a real problem. The universe is not evenly lumpy at every local scale, and gravity from vast concentrations of matter can shape the motion of galaxies across immense distances. Still, it is important not to imagine the Milky Way being dragged by one single mysterious object like a fish on a hook. Cosmic motion is usually the result of many gravitational influences added together, a landscape of pulls rather than one simple rope. The galaxy is responding to the mass around it, visible and invisible, nearby and far away, while space itself expands on the largest scales. This difference between moving through space and being carried by expanding space is subtle but essential. In regions where gravity binds matter strongly, like galaxies and galaxy groups, objects can move toward each other despite cosmic expansion. On much larger scales, galaxies not bound together tend to recede as space expands between them. So, the Milky Way is both a moving galaxy and part of an expanding universe. But those are not the same motion. It is like living in a city on a river inside a country whose borders are also shifting. Local movement and large-scale change overlap, but they do not mean the same thing. The Milky Way's motion also has no front windshield, no clear nose pointed into the dark. A galaxy is not a spaceship with a single engine. It is a rotating, evolving structure of stars, gas, dust, dark matter, and magnetic fields, moving as a gravitational system through a changing cosmic environment. Around it orbit smaller satellite galaxies, some being stretched and stripped by the Milky Way's gravity. Streams of stars arc through the halo, remnants of past encounters and mergers. Gas falls in, gas is pushed out, stars are born, stars die, and the whole galaxy travels while also changing internally. Its journey is not separate from its history. The Milky Way has grown by absorbing smaller systems, and it will continue to be shaped by encounters. Motion, at this scale, is not just translation from one place to another. It is evolution. It is relationship. It is the galaxy becoming itself through everything it passes, pulls, captures, loses, and approaches. And perhaps the most unsettling part is that you cannot step outside this motion to watch it cleanly. You are inside the Milky Way, on a planet around one star, buried within the disk, looking outward through dust and light, trying to reconstruct the movement of the entire system. It is like being inside a drifting cathedral, studying the direction of the building by measuring the changing color of rain on the stained glass. Yet we can do it. We use the motions of galaxies, the redshifts and blue shifts of light, the microwave background, the mapping of cosmic structures, and the behavior of nearby galaxy groups to understand that our galaxy is not still. This should change the way you feel when you look at the night sky. The darkness does not surround a motionless home. It surrounds a moving one. Every quiet evening, every sleeping city, every ocean under moonlight, every mountain under snow, every person believing they are sitting still is being carried by a galaxy moving through the cosmic web. And yet there is no panic in this. The motion is not a disaster. It is the natural state of the universe. Stillness was always the local illusion. The larger truth is layered movement, Earth turning, Earth orbiting, the Sun traveling within the Milky Way moving with the local group flowing through a universe shaped by gravity and expansion. You are nested inside motions you cannot feel, and each larger motion makes the smaller one seem calm. Maybe that is why the thought feels both humbling and strangely comforting. You do not need to feel the journey for the journey to be real. You do not need to see the galaxy moving for it to carry you. The Milky Way is not a fixed backdrop to your life. It is a vessel of stars crossing the deep structure of the cosmos, and you are inside it for a brief moment, looking out from its moving light. Galaxies drift with expanding space. The most distant galaxies are not simply flying away through space. Space itself is stretching the distance between them like a silent fabric growing larger in every direction. This is one of the hardest truths to picture, because your everyday mind understands motion as something moving through a place. A car moves along a road, a bird moves through air, a ship crosses water. But cosmic expansion is different. On the larger scales, galaxies are not all racing outward from one central explosion point inside a pre-existing emptiness. Instead, the distances between widely separated galaxies increase because the scale of space itself changes over time. The universe is not expanding into some outside room, at least not in the way a cloud of smoke expands into air. Space is not a container sitting inside a larger container we can point to. Space is part of the thing expanding. That is why the idea feels so strange. The stage is changing, not just the actors moving across it. If you imagine dots drawn on the surface of a balloon as the balloon inflates, each dot sees the other dots receding, not because the dots crawl across the rubber, but because the rubber between them stretches. The analogy is imperfect, because the universe is not literally the surface of a balloon, and it does not require an outside air-filled room, but it captures one important truth. No dot has to be the center. From any dot, the others seem to move away. This is what astronomers observe in the real universe. Distant galaxies tend to show redshift, meaning their light is stretched toward longer, redder wavelengths by the expansion of space during its journey to us. The farther away a galaxy is, in the broad average pattern, the faster it appears to be receding. This relationship was discovered through the work of astronomers like Edwin Hubble and others, and it became one of the great clues that the universe is not static. Light itself becomes a messenger of this expansion. A photon begins its journey from a distant galaxy, travels across space for millions or billions of years, and while it travels, space stretches. The wavelength of that light stretches with it. By the time it reaches our telescopes, it carries a record of the universe's growth, like a note played long ago that has been lowered in pitch by the swelling of the hall it traveled through. This does not mean every nearby galaxy is moving away from every other nearby galaxy. Gravity can overpower expansion on smaller scales. Galaxies inside clusters can orbit, collide, merge, or fall toward each other because their mutual gravity binds them strongly. The Andromeda Galaxy, for example, is approaching the Milky Way, not receding from it. Planets do not expand away from the Sun. Stars inside galaxies do not drift apart because of cosmic expansion in any ordinary measurable way. Your body does not expand with the universe. Atoms do not stretch as space expands, because electromagnetic forces, gravity, and other binding effects hold local systems together. Expansion becomes clear only across vast cosmic distances, where galaxies are not gravitationally bound to one another in the same local structure. This distinction matters because it prevents a common misunderstanding. The universe is not like bread dough stretching every molecule, every object, every person equally apart. Bound structures remain bound. Expansion is the background growth of distance between large-scale unbound regions. It is the behavior of the cosmic web at enormous scale, not a force tearing apart your room. Yet on those enormous scales the effect is profound. A galaxy so distant that its light has traveled for billions of years may now be far farther away than it was when that light began its journey, because the space between us and it has expanded during the trip. This means looking into deep space is also looking into deep time, but not in a simple static way. You are not seeing distant galaxies exactly where they are now. You are seeing the light they emitted long ago, after that light has been stretched by the evolving universe. The sky becomes an archive of distances that changed while the message was on its way. And this leads to one of the most haunting consequences of expansion. There are galaxies whose light reaches us now, but whose present-day light may never reach us in the far future if cosmic expansion continues accelerating. The universe can contain regions that become causally unreachable, not because they vanish, but because the expansion of space can carry them beyond the range from which new light will ever arrive. In the distant future, observers in some galaxy may see a darker, lonelier sky, with many of today's distant galaxies faded beyond view. Cosmic expansion does not merely move things apart. It changes what can be known. It edits the future visibility of the universe, and the discovery that expansion is accelerating made the story even stranger. For much of the 20th century, many scientists expected gravity to slow the expansion over time. Matter attracts matter, so surely the outward growth should gradually weaken. But observations of distant exploding stars called Type Ia supernovae showed that the expansion is not slowing in the expected way. It is accelerating. Something associated with space itself, often called dark energy, appears to dominate the large-scale behavior of the universe today. We do not fully know what dark energy is. It may be related to a cosmological constant, a steady energy of space, or it may point towards something more dynamic or something missing in our understanding. The honest answer is that the universe is expanding faster over time, and we have a name for the mystery behind that acceleration, but not a final explanation. This is where the science becomes a deep philosophical pressure. You live inside a universe whose largest motion is not an explosion from a center, not a wind blowing galaxies through a void, not a simple outward flight, but the stretching of the distances themselves. It asks you to question what distance means. It asks you to question whether here and there are fixed separations or evolving relationships. Two galaxies may not be moving through space in the ordinary sense, yet the space between them grows. They become farther apart without either one needing to fire an engine, choose a direction, or push against anything. The motion belongs to the geometry. The drift is written into the structure of the universe. And because light has a finite speed, expansion turns the cosmos into a layered memory. Nearby galaxies show us a more recent universe. Distant galaxies show us earlier chapters. The cosmic microwave background shows us an ancient glow from when the universe first became transparent enough for light to travel freely. As space expanded, that ancient light stretched into microwaves, cooling into a faint background that fills the sky. It is not a normal photograph of the beginning, but it is one of the oldest visible records we have, a cooled echo of an early hot state. The fact that this ancient light still surrounds us, stretched by expansion, means the universe carries its own childhood in every direction. And yet even this does not mean the Big Bang was an explosion at one location. The Big Bang describes the early hot, dense state of the observable universe and its subsequent expansion. It happened everywhere in the sense that every region of space was once part of that hot, dense condition. There is no known central point in space from which everything flew away. Every observer in a sufficiently distant galaxy would see, on average, other distant galaxies receding, just as we do. The center is not a place. The expansion is a condition of the whole. That idea can feel almost impossible because human imagination wants a middle, an edge, a direction outward. But the universe is not obligated to fit the architecture of your intuition. It gives you observations first, comfort later, if comfort comes at all. Galaxies drifting with expanding space teach you that motion is not always local, that distance is not always passive, and that the quiet darkness between things may be the most active part of the story. So the next time you look at a deep image of galaxies scattered like sparks across blackness, do not imagine them merely as islands floating in a static sea. Imagine the sea itself changing scale. Imagine light crossing billions of years while its wavelength is stretched by the growth of space. Imagine galaxies becoming unreachable not because they die, but because the universe keeps unfolding between them and us. Imagine a cosmos where the greatest motion is not something you would feel under your feet, but something written into every faraway redshift. The galaxies drift because space expands, and that drifting tells you the universe is not a finished room filled with objects. It is a growing relationship between all distances, a vast and quiet becoming, carrying every visible island of light farther into the dark. Neurons fire even at rest. Your brain does not go quiet when you stop doing something. It begins speaking in a language you usually mistake for silence. Sit still for a moment, close your eyes, and try to do nothing. No talking, no reading, no problem to solve, no hand reaching for a phone. From the outside, your body may look calm, almost paused, as if the mind has stepped away from the controls. But inside your skull, billions of neurons remain active. They are not all firing at once, and they are not firing randomly without purpose. But the brain at rest is far from switched off. Neurons maintain electrical differences across their membranes, adjust chemical signals, respond to internal rhythms, receive quiet inputs from other cells, and sometimes fire action potentials, brief electrical pulses that travel along their branches and influence other neurons. Even when you are not deliberately thinking, your brain is monitoring the body, predicting what might happen next, regulating attention, organizing memories, maintaining your sense of self, and keeping the machinery of consciousness ready. This is one of the most important corrections neuroscience gives to everyday intuition. Rest is not the opposite of activity. Rest is a different pattern of activity. The brain is not like a lamp that is either on or off. It is more like a city at night. The streets may look calmer than during the day, but power grids still hum, hospitals still operate, traffic lights still change, messages still move, and unseen systems keep the whole place alive. A neuron's resting state is also a misleading phrase if you take it too literally. Resting potential does not mean nothing is happening. It means the neuron is maintaining a charged condition, with different concentrations of ions inside and outside the cell. That difference is actively preserved by tiny molecular pumps and channels, especially systems that move sodium and potassium ions across the membrane. The cell is spending energy simply to remain ready. It is holding tension, like a drawn bow that has not yet released. When enough input arrives from other neurons, the membrane voltage can shift until the neuron fires an action potential. That spike travels along the axon and may trigger chemical release at synapses, where one neuron communicates with another. So even before a neuron fires, it is already participating in a delicate electrical economy. Readiness is not emptiness. Silence is not absence. The pause before a signal is also part of the signal's possibility. And at the larger level, the resting brain shows organized patterns that scientists can measure. When people lie quietly in a scanner without performing a specific task, certain brain regions continue to fluctuate together. This is called resting state activity, and it helped reveal networks that remain coordinated even when the mind is not focused on the outside world. One of the most famous is the default mode network, a set of interconnected brain regions, often more active during inward-focused states such as remembering, imagining, self-reflection, and mind-wandering. This does not mean the default mode network is the soul, or that it explains all consciousness, or that it is always doing one simple thing. Real brain networks are complex and flexible, but it does show that doing nothing is not nothing to the brain. When you are quietly staring out a window, your mind may drift into the past, rehearse a conversation, imagine a possible future, evaluate who you are, or connect fragments of experience into a personal story. The body looks still. The brain is building continuity. In fact, the brain consumes a large share of the body's energy even during rest, far more than its size alone would suggest. This energy does not go mostly into dramatic movements or conscious effort. Much of it supports the ongoing maintenance of ion gradients, synaptic communication, background activity, and the constant readiness of neural circuits. Thinking hard can increase energy use in specific regions, but the baseline cost of keeping the brain alive and organized is already high. This is why rest can feel quiet subjectively while remaining metabolically expensive. Your mind is not a blank room waiting for thought to enter. It is an active landscape that must keep itself prepared for perception, movement, memory, emotion, and survival. Some neurons fire spontaneously because their internal properties and network inputs make them rhythmically active. Others fire only when certain conditions are met. Some circuits produce oscillations, coordinated rhythms that can be detected in electrical recordings. These rhythms are not simple music, and they do not mean the brain is operating like a perfect clock. They are shifting patterns of coordination, changing with attention, sleep, memory, movement, and sensory input. Even when you are at rest, your brain is balancing excitation and inhibition. Excitatory signals make neurons more likely to fire. Inhibitory signals make them less likely. Without inhibition, activity could spread uncontrollably. Without excitation, signals would fade into useless stillness. Healthy brain function depends on a moving balance between the two. Attention that allows stability without paralysis, and flexibility without chaos. This balance is so important that disruptions in neural excitability are involved in conditions such as seizures, where excessive synchronized firing can overwhelm normal patterns. So the brain's resting activity is not meaningless noise. It is regulated, constrained, and constantly shaped by the needs of the organism. It also prepares you before you consciously act. Your brain does not wait until the world appears and then begin from zero. It predicts. It maintains models. It compares incoming signals with expectations. It keeps the body mapped, the environment roughly anticipated, and possible actions partly prepared. This is why you can react quickly to a sound, recognize a familiar face in an instant, or catch yourself when you stumble before you have time to narrate what happened. The resting brain is not laziness. It is preparation. It is a background readiness that makes quick perception possible, and this background can shape what you notice. If you are anxious, resting activity may lean toward threat monitoring. If you are grieving, your mind may return again and again to memories and absence. If you are creative, quiet moments may allow distant ideas to connect because the brain is no longer locked onto one external task. Mind wandering can be distracting, but it can also be part of problem solving, planning, and emotional processing. The brain's inner motion is not always efficient, not always pleasant, not always under your control, but it is deeply human. It is the place where memory and possibility keep touching. This also helps explain why true mental rest can feel difficult. You may stop moving, but your neural networks continue to generate thoughts, images, worries, associations, and bodily signals. Meditation, deep breathing, and quiet attention do not turn the brain off. They change how activity is organized and how you relate to it. You are not forcing the ocean to become stone. You are learning to watch the waves without being dragged by everyone. That distinction matters. The goal is not a dead mind. A dead mind would not be peace. Peace is living activity arranged with less struggle. So when you sit still and thoughts continue, it does not mean you have failed at rest. It means your brain is alive, predictive, self-maintaining, and constantly integrating the world you have lived through. Every memory you carry, every habit, every fear, every skill, every word you know is supported by neural circuits that do not simply vanish when you close your eyes. Rest reveals the hidden continuity of the self. It shows that you are not only the thoughts you deliberately choose, but also the background processes that keep returning you to yourself. The brain at rest is like a dark theater after the audience leaves, with stagehands still moving props, lights being tested, old scenes being repaired, and tomorrow's performance quietly prepared. You may not see the work, but without it, the show could not continue. So the next time you sit in silence and assume nothing important is happening, remember the neurons that remain electrically poised, the networks that keep time with one another, the inner systems that monitor your body, the memories that softly reorganize, the predictions that prepare you for the next sound, the next touch, the next thought. Your stillness is not empty. It is supported by a living storm of careful signals, and maybe that is the quiet wonder of the resting brain. Even when you stop reaching for the world inside you keeps moving, keeping you ready to wake, feel, remember, and become. The heart adjusts beat by beat. Your heart is not a drum keeping one perfect rhythm. It is a living instrument that changes its timing from one beat to the next. You may think of the heartbeat as a simple clock inside your chest, steady, loyal, mechanical, repeating the same command again and again until life ends. But a healthy heart is not perfectly regular. It listens, it adjusts, it speeds, slows, hesitates slightly, strengthens, softens, and responds continuously to what your body needs in each passing moment. Even when you are sitting quietly, your heart is not blindly repeating a fixed pattern. It is receiving signals from your nervous system, responding to hormones, reacting to breathing, blood pressure, posture, emotion, temperature, oxygen demand, and the subtle chemistry of your blood. Each beat is part of an ongoing conversation. The heart has its own internal electrical system, beginning in a small cluster of specialized cells called the sinoatrial node, often described as the natural pacemaker. These cells can generate electrical impulses on their own, without waiting for your conscious mind. The signal spreads through the atria, pauses briefly at the atrioventricular node, then travels through pathways that coordinate the ventricles, allowing the chambers to contract in a carefully timed sequence. This timing matters. Blood must move from chamber to chamber, then out toward the lungs and body. If the electrical pattern becomes chaotic, the pumping can weaken or fail. So the heartbeat is not merely a squeeze. It is electrical order becoming muscular movement. It is timing turned into circulation. But the heart's own pacemaker is not left alone. It is constantly influenced by the autonomic nervous system, the part of your nervous system that controls many body functions without conscious effort. One branch, the sympathetic system, tends to increase heart rate and force when the body needs readiness, effort, or alertness. The other branch, the parasympathetic system, especially through the vagus nerve, tends to slow the heart and support recovery, rest, and conservation. These two influences are not simple enemies. They are more like two hands adjusting the same dial with different intentions. When you stand up, blood momentarily shifts downward because of gravity, and your body quickly adjusts heart rate and blood vessel tone to help keep blood flowing to the brain. When you exercise, muscles demand more oxygen and nutrients, carbon dioxide and heat rise, and the heart increases its output, not randomly, but because the whole system recognizes a new need. When you sleep, the rhythm can slow. When you dream, it may become more irregular. When you are startled, it may leap. When you exhale slowly, it may ease. The heart is not emotionally symbolic by accident. It really does respond to the body states that emotions create. Fear can quicken it. Grief can weigh on it. Anticipation can make it flutter. Calm can soften its pace. But this does not mean the heart thinks in the way the brain thinks. It means the heart is deeply wired into the body's regulatory networks. Your feelings are not floating abstractions. They become chemicals, nerve signals, muscle tension, breathing patterns, and cardiovascular changes. The heart is one of the places where inner experience becomes measurable motion. A healthy heartbeat often shows something called heart rate variability, the natural variation in time between beats. This is not the same as a dangerous irregular rhythm. In many contexts, good variability can be a sign that the body is flexible and responsive, able to shift between effort and recovery. A heart that beats like a perfect metronome at every moment might sound reassuring. But biological life is rarely healthiest when it becomes rigid. Living systems adapt. They do not merely repeat, Your breathing, for example, can gently influence heart timing. During inhalation, heart rate may increase slightly. During exhalation, it may decrease slightly. This pattern, called respiratory sinus arrhythmia, is normal in many healthy people and reflects the connection between breath, vagal tone, and cardiovascular regulation. The heart is not separate from the lungs, the vessels, the brainstem, or the blood. It is part of a network. Blood pressure sensors called baroreceptors, located in places such as the carotid arteries and aorta, help monitor pressure and trigger adjustments. If pressure rises, signals can help slow the heart and relax vessels. If pressure falls, the body can increase heart rate and tighten vessels to maintain flow. You are not aware of this second-by-second correction, but without it, standing, walking, bending, resting, and surviving stress would be far more fragile. The heart also changes the strength of its contractions depending on how much blood fills it. When more blood returns to the heart, the muscle fibers stretch more before contracting, and within normal limits, that stretch helps the heart pump more strongly. This principle allows the heart to match output with return, beat after beat, without needing conscious command. It is a beautiful example of built-in responsiveness. The heart feels its own filling through physical conditions and answers with force. At the same time, hormones like adrenaline can increase rate and contraction strength, preparing the body for action. Thyroid hormones, body temperature, hydration, electrolyte balance, medications, illness, and training level can all influence how the heart behaves. An athlete's resting heart rate may be lower because training can make the heart pump more efficiently and increase parasympathetic influence. A fever may raise heart rate because the body's metabolism and demand increase. Dehydration may force the heart to beat faster to maintain circulation when blood volume is reduced. The heartbeat you feel at your wrist is not just a number. It is a summary of conditions inside you. It is your body reporting in pulses what it is trying to manage. And every beat is part of a larger cycle. Blood returning from the body enters the right side of the heart, is sent to the lungs for gas exchange, returns to the left side, then is pumped into the arteries to supply the organs. The coronary arteries supply the heart muscle itself because the pump also needs blood to do its work. This is one of the heart's quiet vulnerabilities. It sustains the body, but it must also sustain itself. If its own blood supply is blocked, the muscle can suffer damage. If its rhythm becomes too disorganized, circulation can collapse. If valves fail, pressure and flow change. The heart is strong but not invincible. It is a responsive organ working within narrow biological limits, endlessly adjusting to preserve life. And perhaps the most astonishing part is how many times it does this without being noticed. Tens of thousands of beats each day, each one slightly shaped by the moment before it and the demand around it. You do not command the heart to accelerate when you climb stairs. You do not manually instruct it to calm when you rest. You do not calculate pressure changes when you stand. Your body does the work beneath awareness, maintaining a moving balance so ordinary that you call it normal. But normal is not simple. Normal is a miracle repeated until it becomes background. So when you place a hand on your chest and feel that pulse, do not imagine a machine knocking in the dark with blind repetition. Imagine an organ listening to the entire body, adjusting beat by beat, answering gravity, breath, fear, sleep, movement, blood, and need. Imagine electricity crossing living tissue, chambers opening and closing, valves guiding flow, nerves whispering faster or slower, pressure sensors sending reports, hormones changing urgency, and muscle translating all of it into motion. The heart is not still between beats. It is preparing, filling, resetting, listening. Its rhythm is not the rhythm of a clock, but the rhythm of adaptation. And maybe that is why the heartbeat feels so intimate. It is not just proof that you are alive. It is proof that life is never a fixed state. Life is adjustment, again and again, one pulse at a time. Cells, repair, molecular damage. Your cells are being damaged every second. And the reason you are still alive is that they are repairing themselves faster than the damage can become a collapse. This is not a dramatic metaphor. It is the quiet biological reality beneath your skin. Every cell in your body lives inside a world of chemical stress, mechanical strain, copying errors, broken molecules, misfolded proteins, leaking electrons, oxidizing compounds, ultraviolet light, heat shifts, toxins, inflammation, and ordinary wear from being alive. Life is not a perfectly preserved machine running in a clean glass chamber. Life is maintenance under pressure. Your cells are not tiny, peaceful rooms where molecules sit neatly in place. They are crowded, wet, busy environments where thousands of reactions happen at the same time, where molecules bump, bind, twist, break, fold, unfold, and sometimes fail. A protein may lose its proper shape. A membrane may become damaged. A mitochondrion may begin producing too many reactive molecules. A lipid may be oxidized. A strand of DNA may be chemically altered. A sugar molecule may attach where it should not. A molecular machine may wear down after repeated use. And yet most of this never becomes noticeable to you, because cells are equipped with repair, cleanup, recycling, and emergency systems that work continuously in the background. The body you feel as one stable self is actually a moving repair project, a living structure preserved by constant correction. One of the main sources of molecular damage comes from oxygen itself. Oxygen is essential for most of your cells because it helps them extract energy from food, especially inside mitochondria. But oxygen chemistry can also produce reactive molecules that damage proteins, lipids, and DNA if they build up too much. These reactive oxygen species are not simply bad in every context. In controlled amounts, cells can use them as signals, but when production exceeds defense, oxidative stress begins. To manage this, cells use antioxidant enzymes and small protective molecules that neutralize reactive compounds before they cause too much harm. This is a careful balance, not a magical shield. Your cells are not trying to eliminate every reactive molecule completely. They are trying to keep the chemistry within a range where life can continue. That distinction matters because biology is rarely about perfect purity. It is about controlled imperfection. Proteins are another major battlefield. A protein must fold into the correct shape to do its job, and that shape can be disturbed by heat, chemical damage, crowding, or random error. A misfolded protein can become useless, sticky, or even dangerous if it starts clumping with others. Cells respond with helper proteins called chaperones, which assist other proteins in folding correctly or refolding after stress. If the protein cannot be saved, the cell may tag it for destruction and send it to a recycling system called the proteasome, where it is broken down into smaller pieces that can be reused. Larger damaged structures, including worn-out cellular components, can be engulfed through a process called autophagy, meaning the cell literally digests parts of itself to recycle material and maintain order. This may sound harsh, but it is one of life's most elegant forms of renewal. The cell survives not by keeping everything forever, but by knowing what must be repaired, what must be dismantled, and what must be replaced. In this way, your cells practice a kind of microscopic wisdom. Not every broken thing should be preserved. Some damage must be transformed back into raw material so something healthier can be built. Mitochondria, the energy-producing structures inside many cells, also require constant quality control. They are essential, but they can be vulnerable because energy production involves intense chemistry. Damaged mitochondria may become less efficient or release harmful signals, so cells monitor them carefully. When a mitochondrion becomes too damaged, it can be removed through a specialized form of autophagy, often called mitophagy. This is not a rare luxury. It is part of how cells protect themselves from internal decline. Your vitality depends not only on making energy, but on removing the damaged engines that make energy poorly. Even the cell membrane, that delicate boundary separating inside from outside, must be maintained. Membranes are made of lipids and proteins, and they can be damaged by oxidation, stretching, toxins, or mechanical stress. Cells can repair small membrane injuries by rapidly rearranging lipids, bringing in vesicles, or removing damaged patches. The membrane is not a plastic bag around life. It is an active border, full of channels, receptors, signals, and repair responses. It decides what enters, what leaves, what is recognized, what is ignored, and when danger has touched the cell. If that border fails, the cell can lose control of its inner chemistry, so even the edge of a cell is under constant care. And when damage becomes too much, when repair systems cannot restore stability, cells do not always continue blindly. Some may enter a state called senescence, where they stop dividing but remain alive, often sending signals that can affect nearby tissue. Others may initiate programmed cell death, a controlled self-destruction called apoptosis. This is not failure in the simple sense. Sometimes the healthiest choice for the organism is for a damaged cell to remove itself before it becomes dangerous. A cell that cannot repair itself properly and keeps dividing can become a threat. This is why repair is tied to cancer prevention, aging, immunity, inflammation, and tissue health. Your body is not only trying to keep cells alive, it is trying to keep the right cells alive in the right condition. Survival without quality control would not be health. It would be disorder. The astonishing thing is that all of this happens without your awareness. You do not feel a protein being refolded. You do not feel a damaged mitochondrion being recycled. You do not feel an antioxidant enzyme neutralizing a reactive molecule. You do not feel a membrane patch being repaired, or a cell deciding whether to recover or shut itself down. You experience yourself as continuous, but that continuity is built from invisible corrections. The body is like a city whose roads crack. Wires fray, pipes leak, walls weather, and machines overheat. Yet repair crews move through it day and night, fixing, removing, replacing, cleaning, and rebuilding so smoothly that the citizen inside the city believes nothing has changed. But everything is changing. Every day, your cells are negotiating with damage. Every day, repair succeeds often enough that you remain coherent. And when repair becomes slower, weaker, or overwhelmed over time, the effects can contribute to aging and disease. Aging is not caused by one single kind of damage, and it is not simply the body running out of time. It involves many interacting processes: accumulated molecular damage, changes in repair capacity, altered cell signaling, mitochondrial dysfunction, protein quality control problems, inflammation, stem cell changes, and more. The body does not age because one switch flips. It ages because maintenance becomes harder across many levels at once. This makes life feel more fragile but also more impressive. You are not a static object slowly wearing down. You are a self-repairing pattern, constantly resisting disorder, constantly paying energy to remain yourself. Food, sleep, movement, stress, toxins, sunlight, infection, and time all influence the burden placed on repair systems. This does not mean you can control everything, and it does not mean disease is always a personal failure. Biology is too complex and too uneven for that. But it does mean your cells are always living in relationship with conditions. They are always responding to the world you place them in, the resources available to them, and the stresses they must endure. There is something deeply humbling in that. Your life depends on work you never see, performed by structures too small for your imagination to hold clearly. You are alive because damage is not always final. A broken molecule can be repaired. A flawed protein can be refolded or recycled. A worn-out component can be removed. A dangerous cell can be stopped. Life is not the absence of breaking. Life is the art of not letting breaking have the last word too soon. So when you think of your body as still, as stable, as simply there, remember the hidden maintenance beneath that feeling. Remember that every quiet moment is supported by molecular repair crews moving through the dark interior of your cells. Remember that you are not preserved by stillness, but by correction. You are not a statue made of flesh. You are a living negotiation against damage, a pattern rebuilt from within, a temporary order maintained by countless acts of microscopic care. And perhaps that is the soft truth this science leaves behind. To be alive is not to remain untouched. It is to be touched by damage again and again, and still for a while to repair enough to continue. Proteins fold and unfold. A protein is born as a chain, but it only becomes alive in the body when that chain learns how to become a shape. Inside every cell, proteins begin as long strings of amino acids, assembled according to genetic instructions, one unit after another, like letters being placed into a sentence that has not yet learned how to fold itself into meaning. But a protein is not useful simply because its parts are in the right order. Its power comes from the way that order bends, twists, packs, flexes, and settles into a three-dimensional form. Shape is function. A protein that cuts molecules, carries oxygen, senses light, builds muscle, copies information, receives signals, or helps a cell move can only do its job because certain surfaces, pockets, charges, and flexible regions end up in the right places. If the sequence is the script, folding is the performance. And the performance is astonishingly delicate. The chain does not fold by a tiny hand, arranging every piece from the outside. It folds because the amino acids interact with water, with one another, and with the chemical environment around them. Some parts prefer to hide away from water, gathering toward the interior. Some parts are comfortable facing outward. Some form local patterns like coils or sheets, stabilized by small attractions. Some regions bend sharply. Some remain loose. The final structure emerges from countless small preferences combining into a larger form, like a crowd finding a stable arrangement without anyone shouting instructions. This is one of biology's quiet miracles. A microscopic chain, guided only by physical chemistry, can collapse into a precise machine. But it is not always a single rigid machine. That is the first misconception to let go of. Proteins are not little statues. They breathe. They flex, they open and close, they shift between related shapes, they tremble around their preferred forms, and that movement is often essential to their work. An enzyme may change shape slightly when it binds a molecule, bringing key parts into position so a reaction can happen. A receptor in a cell membrane may alter its structure when a signal arrives, transmitting information from outside the cell to the inside. Hemoglobin, the protein that helps carry oxygen in red blood cells, changes its shape as oxygen binds, making it easier for more oxygen to attach and later easier to release it where tissues need it. This means folding is not just about reaching a final frozen form. It is about entering a landscape of possible forms, some more stable, some temporary, some active, some inactive. A protein lives by moving within that landscape. Too stiff, and it cannot respond. Too loose, and it cannot hold function. Life depends on structure with flexibility, order with motion, stability with the ability to change. This is why unfolding is not simply failure. Sometimes a protein partially unfolds as part of its normal behavior. Some proteins are designed to be flexible. Some even exist as intrinsically disordered proteins, meaning they do not settle into one stable shape under normal conditions. Yet they still perform crucial roles, especially in signaling, regulation, and interactions with other molecules. This breaks the old idea that every useful protein must be folded into one neat, permanent structure. Biology is more creative than that. Some proteins are like keys with fixed shapes. Others are like soft hands that change their grip depending on what they touch. Disorder, in the right context, can be functional. Flexibility can be information. A loose chain can become meaningful when it meets the right partner, but unfolding can also become dangerous when the wrong conditions push a protein away from its usable form. Heat, extreme acidity, unusual salt levels, chemicals, radiation, or genetic changes can disrupt the attractions that hold a protein in shape. This is what happens when an egg white turns opaque during cooking. The heat causes proteins to unfold and then tangle with one another, creating a new structure that cannot simply return to its original state when cooled. Cooking is chemistry made visible. The clear liquid becomes white and firm because proteins have changed shape and linked into a different network. The same principle appears when milk curdles, when hair changes with heat or chemicals, when enzymes stop working after being overheated, or when fever becomes dangerous if the body's temperature rises beyond safe limits. Your body relies on proteins having the right shape, and shape depends on conditions. The world inside a cell must remain within boundaries because molecular form is fragile. But fragility is not weakness. Fragility is the price of precision. A stone can be stable because it does very little. A protein must be delicate because it must do almost everything. It must recognize one molecule among many, speed a reaction without being consumed, transmit a signal without confusing it, assemble into larger structures without clumping randomly, and sometimes disassemble when its job is done. Every protein is a small negotiation between reliability and responsiveness. The folding process itself is also far more efficient than it first appears. If a protein had to test every possible shape one by one, it could take impossibly long to find the right form. But proteins do not search blindly through every arrangement. Their sequence creates tendencies. Local parts begin forming patterns, unfavorable shapes are avoided. Favorable interactions guide the chain downhill through a kind of folding landscape, often described as a funnel, where many possible starting motions lead toward more stable forms. This image is useful because it shows that folding is not a straight line and not pure randomness. It is guided wandering. The chain explores, collapses, adjusts, and settles, often with help from the surrounding environment. In living cells, the situation is even more crowded and difficult than in a clean laboratory tube. The cell is packed with other molecules, membranes, compartments, and ongoing reactions. A newly made protein has to fold in a busy city, not an empty room. Some proteins fold as they are being made, while the chain is still emerging from the ribosome. Others need assistance, protection, or controlled conditions to avoid wrong interactions. But the deeper point is not the assistance itself. It is that folding is a physical event happening in real time inside you, over and over, at every moment. Your body is not just made of proteins. Your body is continually producing proteins, shaping them, using them, changing them, and replacing them. And when protein folding goes wrong in certain ways, the consequences can be severe. Misfolded proteins may lose function, but some can also form aggregates, clumps, or amyloid structures associated with diseases. In prion diseases, misfolded proteins can encourage other copies of the same protein to misfold, spreading a harmful shape like a corrupted pattern. In neurodegenerative diseases, abnormal protein aggregation is one of the major areas of research, though these diseases are complex and cannot be reduced to one simple cause. Still, the lesson is clear. Shape can carry biological meaning, and wrong shape can become biological danger. A molecule does not need to be alive to spread disorder. Sometimes a form is enough. This makes protein folding one of the strangest bridges between chemistry and life. There is no consciousness in the chain. No little mind decides where to bend. Yet from these bends come muscles that move, eyes that detect light, immune systems that recognize invaders, enzymes that digest food, hormones that signal change, and structures that let cells hold themselves together. The body's intelligence is not located only in the brain. At a molecular level, intelligence often looks like fit. The right shape meeting the right partner at the right time. The hand fits the tool. The key fits the lock. The folded surface fits the molecule it must recognize. And beneath every fit is a history of physical forces, genetic sequences, evolution, and cellular conditions. You are alive because countless chains of atoms fold into useful forms before falling apart. Because matter can become machinery without becoming metal. Because softness can become precision. So when you think of your body, do not imagine it as a fixed object made once and preserved. Imagine a vast interior origami, millions of molecular chains becoming shapes, relaxing, tightening, opening, closing, binding, releasing, sometimes unfolding, sometimes refolding, sometimes becoming something entirely new. A protein is not merely a chemical. It is a sentence that must become architecture. It is a line that must become a tool. It is motion disciplined into form. And perhaps that is the quiet truth proteins leave with you. Life is not only written in codes, but folded into shapes. What you are depends not just on what your molecules are made of, but on how they bend into meaning. DNA is constantly copied and repaired. Every time a cell prepares to divide, it must copy a library so enormous and so fragile that a single misplaced letter can change the future of living tissue. DNA is often described as a blueprint, but that word can make it sound too calm, too clean, too finished, as if your genetic information was stored in a locked vault where nothing ever touches it. The real story is much more active. DNA is a long molecule carrying instructions in the sequence of its chemical bases. And inside your cells, it is not just sitting in darkness like an ancient scroll. It is being read, folded, unpacked, copied, checked, damaged, repaired, and protected. Every dividing cell faces a remarkable task. Before it becomes two cells, it must duplicate its DNA so each new cell receives a complete set of genetic information. This copying process is called DNA replication, and it is one of the most precise operations in biology. But precision does not mean perfection without effort. The DNA double helix must be opened, the two strands separated, and each strand used as a guide to build a matching new strand. Specialized enzymes move along the DNA, adding the correct building blocks according to pairing rules. Other proteins unwind the helix, stabilize the open strands, relieve twisting stress, remove temporary primers, connect fragments, and help coordinate the whole process. It is not one molecule doing one job. It is a moving molecular workshop, a team of machines working at high speed inside a space too small for your imagination to comfortably enter. And yet, because the genome is so large, even a very accurate copying system would be dangerous if it had no way to correct itself. The main copying enzyme can proofread as it works, recognizing many mistakes and removing the wrong base before continuing. After replication, another layer of correction called mismatch repair can find errors that escape the first proofreading step. Identify the newly made strand, remove the incorrect section, and fill it in properly. This means DNA copying is not just writing, it is writing with built-in editing. The cell does not trust the first draft completely. It checks, it revises, it compares. It protects continuity by refusing to assume that speed alone is enough. But replication errors are only one threat. DNA is also damaged by ordinary chemistry. Bases can change shape, break away, oxidize, or become chemically modified. Ultraviolet light from the sun can cause neighboring DNA bases to link abnormally, bending the structure and interfering with reading or copying. Certain chemicals can attach to DNA or break it. Radiation can damage the strands. Normal cellular metabolism can produce reactive molecules that strike DNA. Sometimes one strand breaks. Sometimes both strands break, which is much more dangerous because the cell can lose the original guide needed for accurate repair. So cells carry multiple repair systems, each specialized for different kinds of damage. Base excision repair handles small chemical changes to individual bases. Nucleotide excision repair removes bulkier distortions, including damage caused by ultraviolet light. Single-strand break repair deals with cuts in one strand. Double-strand breaks can be repaired by methods such as homologous recombination, which uses an undamaged copy as a template when available, or non-homologous end joining, which reconnects broken ends more quickly, but can sometimes introduce changes. These names sound technical, but the idea is deeply understandable. DNA is too important to have only one emergency plan. The cell has a toolkit, and the repair method depends on the kind of injury, the cell's condition, and whether a reliable template is available. This is not a perfect system. Some damage is missed. Some repairs introduce small errors. Some mutations remain and are passed on when the cell divides. And not all mutations are automatically disasters. Many have little effect. Some are harmful. Rarely, across evolutionary time, mutations can contribute to new traits. Life depends on a strange balance. DNA must be stable enough to preserve identity, but not so frozen that change becomes impossible. Too much damage and cells fail or become dangerous. Too little variation across generations, and evolution would have no raw material. The genome is therefore not a sacred text kept untouched by time. It is a living archive maintained through repair, yet never completely isolated from change. This tension is one of the deepest truths of biology. Your body survives because it protects its instructions, but life itself has diversified because those instructions can sometimes alter. In your own lifetime, however, the priority inside most cells is not evolution. It is maintenance. A skin cell exposed to sunlight, a cell lining the intestine, an immune cell multiplying in response to infection, a stem cell renewing tissue, all must guard their DNA carefully. If damage becomes too severe, cells can pause division to allow repair. If the damage cannot be repaired safely, some cells may activate self-destruction pathways rather than risk passing corrupted information onward. This is one reason the body has tumor suppressor systems, proteins that help monitor damage and prevent unstable cells from dividing uncontrollably. Cancer can arise when mutations accumulate in genes that control growth, repair, or cell death, allowing cells to ignore normal restraints. This does not mean every DNA mistake causes cancer, and it does not mean cancer has one simple cause. It means that genetic maintenance is one of the barriers standing between ordinary cell life and dangerous disorder. Every healthy day depends partly on countless cells choosing not only to live, but to live accurately. Even the ends of chromosomes require special care. Linear chromosomes have protective caps called telomeres, which help prevent chromosome ends from being mistaken for broken DNA. Because of the way DNA copying works, telomeres can shorten in many dividing cells over time. This shortening is connected to cell aging and division limits, though the story is complex and differs between cell types. Some cells, such as stem cells and many cancer cells, use an enzyme called telomerase to help maintain telomeres. Here again, biology refuses to become simple. The same kind of mechanism that helps certain cells preserve long-term function can become dangerous if misused by cells that should stop dividing. Repair, copying, protection, and growth are never isolated virtues. They must be regulated. Too little repair can invite damage. Too much survival in the wrong cell can become disease. The body is not trying to make every cell immortal. It is trying to maintain the organism. And perhaps this is what makes DNA so haunting. It is both personal and impersonal. It carries instructions that helped build your eyes, your skin, your enzymes, your tissues, and many of your inherited traits. Yet the molecule itself is not aware of you. It does not know your name. It does not remember your childhood. It is chemistry shaped by billions of years of life, copied through generations with astonishing fidelity and occasional change. Every cell that divides inside you participates in a chain of copying older than humanity, older than language, older than every civilization. The same basic need repeats again and again. Preserve the message, repair the damage, pass on the information, but allow just enough possibility for life to keep adapting. So when you think of your body as still, remember that in dividing cells, DNA is being unwound and copied. In damaged cells, repair proteins are searching for errors. In sunlit skin, ultraviolet scars are being recognized. In tissues renewing themselves, genetic instructions are being duplicated with care. You are not held together by a flawless book locked away from the world. You are held together by a book that is constantly handled, read, copied, corrected, and defended. And maybe the quiet lesson is this. Continuity is not the same as untouched perfection. Continuity is maintenance, identity is repair. Life persists not because its instructions never suffer damage, but because again and again, in the darkness of the cell, something notices the broken letter and tries to write it right. Blood cells travel continuously. A single red blood cell has no eyes, no brain, and no sense of destination. Yet it spends its life traveling through you, like a tiny messenger in a river that never closes. Your blood may look like a simple red liquid when you see it outside the body, but inside you, it is not merely fluid. It is a moving population of cells, proteins, nutrients, gases, signals, waste products, and fragments of repair, all carried through a branching network of vessels so vast and narrow that it reaches almost every living corner of you. The red color comes mostly from red blood cells packed with hemoglobin, the iron-containing protein that binds oxygen in the lungs and releases it in tissues that need it. But these cells are not little red spheres drifting lazily through open pipes. Mature human red blood cells are shaped like flexible discs with thinner centers, a form that gives them a large surface area and helps them bend through capillaries smaller than they are. This is one of the quiet miracles of circulation. the cell must deform to continue. It squeezes, folds, stretches, and slides through microscopic passages, then springs back again, over and over, without tearing itself apart. It has no nucleus in its mature form, which gives more space for hemoglobin and makes it more flexible, but also means it cannot repair itself in the same way many other cells can. It is built for a mission, stripped down for carrying, shaped by function rather than comfort. And for around 120 days, a typical red blood cell keeps moving, passing through arteries, arterioles, capillaries, venules, veins, lungs, and tissues in repeating journeys. It does not choose where to go. Pressure gradients, vessel width, branching paths, and the needs of tissues guide its motion. In large vessels, blood flows as a coordinated stream, but in the smallest capillaries, red blood cells may pass almost single file, bringing oxygen close enough to cells for exchange to happen efficiently. A muscle fiber during exercise, a neuron demanding energy, a kidney filtering blood, a patch of skin warming or cooling, all depend on the arrival and departure of these traveling cells. Oxygen leaves the red blood cell not because someone commands it, but because local conditions favor release. Tissues with lower oxygen, higher carbon dioxide, greater acidity, or more warmth can encourage hemoglobin to let go of its cargo more readily. This means blood delivery is not just transportation. It is responsive chemistry. The red blood cell carries oxygen through the highway, but the tissue environment helps decide when the cargo should be unloaded. At the same time, carbon dioxide produced by cells enters the blood in several forms, much of it converted into bicarbonate in a process helped by enzymes inside red blood cells. So these cells are not only oxygen carriers, they are also part of the body's system for managing carbon dioxide and acid-base balance, helping keep the inner environment within a range where life can continue. White blood cells travel too, but their journey has a different meaning. They are not primarily cargo carriers. They are defenders, inspectors, responders. Some circulate through blood and lymph, while others move into tissues, searching for signs of infection, damage, or abnormal cells. They can slow down near vessel walls, attach to the inner lining, squeeze between cells of the vessel wall, and enter tissue where they are needed. This movement is guided by chemical signals released from injured or infected regions. In that sense, blood is not just a river, it is an alert system. When something goes wrong in one part of the body, signals can call immune cells toward the problem, turning circulation into communication. Platelets, small cell fragments involved in clotting, also travel continuously, quietly watching for damage in vessel walls. When a vessel is injured, platelets can adhere, activate, and help form a plug while clotting proteins build a stronger seal. This is another balance the body must manage carefully. Too little clotting and bleeding becomes dangerous. Too much clotting in the wrong place, and a vessel can be blocked. The bloodstream is therefore always balancing flow and repair, movement and sealing, openness and protection. Plasma, the liquid part of blood, carries dissolved salts, hormones, nutrients, antibodies, clotting factors, proteins, heat, and waste products. It helps distribute what the body needs and remove what the body must process or excrete. Glucose moves toward hungry tissues. Hormones travel from glands to distant targets. Waste molecules move toward organs such as the kidneys and liver for handling. Heat generated in active tissues is carried through blood and redistributed, helping regulate body temperature. The bloodstream is not a single-purpose delivery service. It is a moving interior climate, a transport network, a defense route, a waste pathway, a signal highway, and a repair system all at once. And the vessels themselves are not passive tubes. Their inner lining, the endothelium, senses flow, releases signals, helps regulate vessel tone, influences clotting, and participates in inflammation. Blood moving across this living surface creates shear forces that cells can detect. Vessels can widen or narrow depending on local needs and nervous or chemical signals, directing more blood toward active tissues and less toward regions that can wait. After a meal, more blood supports digestion. During exercise, working muscles receive more. In cold conditions, surface vessels may constrict to conserve heat. In warmth, they may widen to release it. This means the path of blood is never just a fixed plumbing diagram. It is a changing distribution system, adjusting moment by moment to the body's priorities. In the bone marrow, new blood cells are constantly being produced through hematopoiesis, a process that turns stem and progenitor cells into red blood cells, white blood cells, and platelets. Old or damaged red blood cells are removed mainly by the spleen and liver, where their components can be broken down and recycled. Iron can be reused. Hemoglobin is dismantled. The cell's journey ends, but its materials do not simply vanish. They re-enter the body's economy. This is one of the most beautiful truths hidden in blood. Circulation is not only movement through space, it is movement through cycles of birth, service, breakdown, and reuse. A blood cell is made, travels, performs, ages, and is taken apart so its pieces can help build or support something else. Your body is not just carrying blood, it is continually renewing the travelers inside it. And perhaps that is why blood feels so symbolically powerful across cultures. It is not only red fluid, it is motion made intimate. It is the evidence that your body is not a statue, not a sealed object, not a still container of organs. You are a landscape of routes. You are full of rivers too narrow to see, couriers too small to imagine, checkpoints, signals, crossings, repairs, and returns. Even when you lie perfectly still, red blood cells are squeezing through capillaries. White blood cells are patrolling. Platelets are waiting. Plasma is carrying messages. Marrow is producing replacements, and the spleen is filtering out worn travelers. The stillness of your body is supported by a circulation that cannot stop for long without consequences. If flow is blocked, tissue suffers. If oxygen delivery fails, cells struggle quickly. If bleeding removes too much volume, pressure falls and organs are threatened. Life depends on movement that is constant but precisely managed. So the next time you feel your pulse in your wrist, do not think only of a beat. Think of the travelers released by that pressure wave. The red cells folding through microscopic passages, the immune cells listening for chemical alarms, the platelets ready to seal a broken wall, the plasma carrying warmth and messages through hidden roads. Blood cells travel continuously, not because motion is dramatic, but because stillness would be impossible for a body that must feed, defend, clean, repair, and remember itself chemically. Inside you, the river is always moving, and every quiet moment you survive is carried by cells that never get to rest. Sleep still runs body systems. Sleep looks like surrender from the outside, but inside the body it is one of the most organized periods of work you will ever enter. You lie down, close your eyes, stop speaking, stop walking, stop reaching into the world, and it feels as if life has dimmed its lights. To anyone watching, you may seem almost absent, reduced to breathing, warmth, and a shape beneath a blanket. But sleep is not the body turning off. It is a change in operating mode. The brain, hormones, immune system, metabolism, muscles, temperature control, memory circuits, and tissue maintenance all shift into patterns that waking life cannot fully replace. This is why sleep is not optional decoration added to survival. It is biological infrastructure. During the night, your body moves through cycles, including non-REM sleep and REM sleep, each with different kinds of activity. In deeper non-REM sleep, brain waves become slower and more synchronized. Heart rate and breathing often settle, and the body enters a state strongly associated with restoration, energy regulation, and certain forms of memory processing. In REM sleep, the brain becomes more active in particular ways. Dreams often become vivid, the eyes move rapidly, and most skeletal muscles are temporarily inhibited so you do not act out your dreams. The sleeping body is therefore not in one simple state. It is traveling through stages, each with its own purpose, like a night crew moving through different rooms of a building, repairing one system, checking another, dimming lights here, increasing activity there. One of the most fascinating processes linked to sleep is the brain's waste-clearing activity. During sleep, especially deep sleep, the brain's fluid systems appear to help remove metabolic waste products more effectively than during waking. Researchers often describe this as part of the glymphatic system, a network involving cerebrospinal fluid moving through spaces around brain cells and helping clear waste. The details are still being studied, but the basic idea is powerful. The brain does not only need sleep to rest from thought, it may need sleep to maintain its physical environment. Waking consciousness produces activity, and activity produces byproducts. Sleep helps manage the cost of being awake. This changes the emotional meaning of tiredness. Fatigue is not just weakness, it can be the body asking for maintenance time. Sleep also supports memory, but not like a computer simply saving a file. Memories are not copied into storage in one clean step. During sleep, the brain appears to reactivate, strengthen, weaken, reorganize, and integrate different kinds of information. Some memories become more stable. Some emotional experiences are processed. Some irrelevant details may fade. Skills and patterns can be refined. The sleeping brain is not merely replaying the day like a film. It is editing the nervous system's relationship to the day. This is why a problem can feel different after sleep, why learning often improves after rest, why emotional pain may shift with time and dreaming, and why chronic sleep loss can disturb attention, mood, judgment, and memory. You are not only awake when you learn in part by leaving the world and letting the brain reshape what the world has done to you. Hormones also follow sleep-related rhythms. Growth hormone is released strongly during certain periods of deep sleep, supporting tissue repair, metabolism, and development. Cortisol, often associated with alertness and stress regulation, follows a daily rhythm that usually rises toward morning, helping prepare the body to wake. Melatonin, produced in response to darkness by the pineal gland under control of the body's internal clock, helps signal night to the body, though it is not a simple knockout chemical. Insulin sensitivity, appetite hormones, and glucose regulation are also influenced by sleep. This is why poor sleep can affect hunger, blood sugar control, weight regulation, and energy balance. The body does not separate sleep from metabolism. It uses sleep as part of its timing system. Your cells need to know not only what to do, but when to do it. That timing is guided by circadian rhythms, internal biological clocks influenced strongly by light and darkness. These rhythms help coordinate body temperature, hormone release, digestion, alertness, and many other functions across the day and night. When sleep is mistimed, such as during jet lag, shift work, or irregular schedules, the body can feel confused because different systems are no longer aligned. You may be lying in bed while parts of your biology still think it is daytime, or forcing yourself awake while your internal night has not ended. Sleep is therefore not only about duration. Timing matters, regularity matters, light exposure matters. The body is not a machine that can be charged at any random hour with the same result. It is a living clockwork of chemistry, and sleep is one of its deepest time signals. The immune system also changes during sleep. Certain immune activities are influenced by sleep duration and quality, and sleep can support the body's ability to respond to infection and vaccination. When you are sick, sleepiness is not just inconvenience. It may be part of the body's response, redirecting energy and behavior toward recovery. Fever, inflammation, immune signaling, and sleep interact in complex ways. This does not mean sleep alone cures illness, and it does not mean more sleep is always better in every situation, but it does mean that the sleeping body is not passive. It is coordinating defense. While you are unconscious, cells communicate, signals rise and fall, tissues adjust, and the body decides where resources are needed. Even temperature changes. Your core body temperature usually drops during sleep, helping support the transition into rest. Blood flow patterns shift. Muscles relax. Breathing changes with sleep stage. Digestion slows in some ways but does not stop. The liver continues metabolic work. The kidneys keep filtering, though urine production often changes overnight. Skin repairs, tissues rebuild, and energy use is regulated. The body is not waiting for morning to resume life. Morning is possible because the night did not stop working. Dreams add another layer to the mystery. They are not fully understood, and not every dream has a hidden message in the dramatic sense people often imagine. But dreaming shows that the sleeping mind is not blank. It can generate images, emotions, narratives, threats, absurdities, memories, and impossible combinations. Some dreams may reflect emotional processing, memory fragments, brain activation patterns, or attempts to create coherence from internal signals. A dream can feel like a private universe because the brain can simulate experience without outside input. Yet while you dream, your body is carefully regulated so that most movements are suppressed during REM sleep. This protection is remarkable. The brain creates worlds. The body prevents most of them from becoming dangerous actions. Sleep is not a collapse into disorder. It is controlled vulnerability. You are unconscious but not abandoned. Systems guard the boundary between dream and movement, between rest and survival. And that vulnerability is part of what makes sleep so profound. Every night, you disappear from the waking world for hours. You release control. You trust the body to keep breathing, to keep circulating blood, to keep regulating temperature, to keep repairing, to keep returning you to consciousness. You practice a small surrender that life requires again and again. Modern culture often treats sleep as wasted time, as if every hour not spent producing, watching, scrolling, or working is an hour lost. But biology disagrees. Sleep is not the enemy of productivity. It is one of the conditions that makes coherent waking possible. Without enough sleep, attention frays, emotional control weakens, reaction time slows, memory suffers, immune function can be affected, and the body's regulation becomes less stable. You may still be awake, but wakefulness without restoration becomes a thinner version of life. So when you see someone sleeping, do not imagine emptiness beneath closed eyes. Imagine a body running quiet systems with extraordinary precision. Imagine the brain clearing waste, sorting experience, altering memory traces, and moving through stages. Imagine hormones rising and falling like tides within the blood. Imagine immune signals being adjusted, tissues being repaired, temperature being lowered, dreams being built and contained, and the internal clock preparing the next return to daylight. Sleep is stillness only from the outside. Inside, it is maintenance, timing, protection, and renewal. And perhaps that is the soft lesson hidden in every night. Life does not continue because you are always awake and in control. Life continues because, for a while, you let go, and the body keeps the universe of you quietly running in the dark. Stillness is a human speed illusion. Stillness may be the most convincing illusion your body ever learned to trust. You sit in a quiet room, look at a chair, a wall, a sleeping face, a stone on a windowsill, and everything seems paused, as if the world has agreed to hold its breath for you. But what you call stillness is not a universal truth. It is a judgment made by a nervous system built for a narrow range of speeds. Your eyes, ears, skin, and brain evolved to notice the kinds of motion that mattered for survival. An animal moving in the grass, a falling branch, a hand reaching toward you, a fire spreading, a face-changing expression, a shadow approaching too quickly. Motions much faster than your senses can resolve blur into continuity, while motions much slower than your life can follow harden into permanence. This is the hidden trap. You do not see motion as it truly is. You see motion that fits your timing. A hummingbird's wings become a haze because they move too quickly for ordinary vision to separate every beat. A plant growing becomes invisible because it moves too slowly for your patience. A glacier creeping down a valley seems frozen until time-lapse photography reveals it flowing like a thick, ancient river. A building settling, a coastline shifting, a tree thickening, a face aging, a scar fading, a city expanding. All of these may be forms of motion that disappear into the blind spots of human speed. Your senses are not lying to you maliciously. They are simplifying. They compress the world into a version you can act inside. If you perceived every microscopic vibration, every chemical exchange, every cellular adjustment, every tectonic strain, every slow deformation, every flicker too brief for thought, you would not gain truth in a usable form. You would drown in detail, so the brain filters, it smooths, it averages, it turns countless tiny changes into stable objects and manageable scenes. The result is the calm world you can walk through. But that calm is an edited version, not the whole film. Think of a movie. It is made of separate frames, still images shown quickly enough that your brain experiences motion. Now reverse the idea. The real world is full of continuous change. But if a change is too slow compared with your attention, your brain experiences it as stillness. You live between these two illusions. Fast change becomes smooth motion. Slow change becomes no motion at all. This is why a mountain seems permanent, while a flame seems alive. The mountain changes too, but its changes are written in a script too slow for the human heartbeat. The flame changes fast enough to feel present. Your body turns time into meaning by deciding what matters now. That now is not a law of the universe. It is a biological window. Even your sense of a stable present is constructed. Light reaches your eyes, sound reaches your ears, touch reaches your skin, and the brain gathers these signals, processes them, aligns them, and gives you a moment that feels immediate. But immediate does not mean raw. Perception takes time. The brain must decide what belongs together, what moved, what changed, what should be ignored, what might be dangerous. In that processing, some changes are sharpened and others are erased. You notice a sudden movement in the corner of your eye because sudden movement may matter. You do not notice the slow drift of shadows across a room until you look back and realize the light has changed. You do not feel your hair growing, your nails lengthening, your cells replacing molecules, your bones remodeling, your memories softening with each recall. Yet all of these are forms of motion in the broadest sense. Matter rearranging, structure changing, information updating, energy being used, patterns being maintained. Stillness is often just change below the threshold of attention. There is another layer too. Motion depends on reference. Sitting on a train that moves smoothly, you may feel still because your body, seat, phone, coffee cup, and nearby passengers share the same motion. Look outside and the landscape reveals the travel. Without comparison, motion can hide. This is true not only in vehicles, but in life itself. You feel stationary because everything familiar moves with you. Your room, your habits, your social world, your planet, your era. Only when something outside your frame appears do you notice the drift. A childhood photograph shows time moving through your face. A long-closed neighborhood reveals that a city was never still. A fossil shows that life has been changing beyond memory. A telescope shows that the sky is not a ceiling, but a history of moving light. Reference points awaken motion. Without them, change becomes background. This is why tools have expanded human reality. Microscopes reveal movements too small to see. Telescopes reveal motions too distant to notice. High-speed cameras stretch fast events into understandable sequences. Time-lapse compresses slow events into visible flow. Seismometers detect tremors you cannot feel. Atomic clocks measure shifts beyond ordinary intuition. Satellites track drifting land, rising seas, moving storms, shrinking ice, and changing vegetation. Instruments do not invent motion. They rescue it from the limits of the body. They show that still often means not moving at my scale. And this realization should make you humble, because it means reality is not organized around human perception. The universe does not owe you speeds that are easy to understand. Some processes unfold in fractions of a second. Others require centuries, millions of years or longer. Some are too small to touch, others too vast to feel, and yet all belong to the same moving world. Even silence participates in this illusion. A quiet room may contain electrical activity, heat exchange, air currents too slight to notice, materials expanding and contracting subtly, bodies regulating themselves, dust settling, pressure changing, light reflecting, signals passing through wires and walls. Stillness is not emptiness. It is a local truce between your senses and the changes they choose not to report. And emotionally, this can feel unsettling. You want stillness to be real because stillness gives comfort. It lets you believe there are solid places, fixed identities, final answers. It lets you rest your mind on objects and say, this is here, this remains. But science keeps whispering that remaining is often active work. A living body remains alive by changing. A memory remains meaningful by being reconstructed. A society remains recognizable while people enter and leave. Buildings rise and fall. Languages shift and values transform. Even the self you call you is not motionless. It is a continuity made from renewal, habit, memory, sensation, and adjustment. You feel like one stable person because change happens in layers. Some fast, some slow, some hidden, some remembered only afterward. The illusion of stillness is not useless. It is merciful. It gives the mind a surface to stand on. But if you mistake the surface for the whole truth, you miss the deeper beauty. The world is not a warehouse of fixed things. It is a pattern of processes temporarily stable enough to be named. A chair is wood, joints, fibers, pressure, age, temperature, and use, held in a form for a while. A body is circulation, repair, signaling, breathing, digestion, thought, growth, decay, and renewal, held in a form for a while. A landscape is uplift, erosion, water, roots, weather, and time, held in a form for a while. To name something is to pause it in language, but reality itself does not pause. It only appears to pause when its motion is too balanced, too slow, too fast, too shared, or too small for you. So the next time you feel the world sitting calmly around you, do not rush to destroy that calm. Let it soothe you, but behind it, remember the deeper truth. Stillness is the translation your human speed body gives to motions it cannot follow. You are living inside a universe of movement, but you are tuned to one small band of the song. And maybe wisdom begins when you can hold both truths at once. The room is still enough for you to rest, and yet nothing in it is truly motionless. The silence is real as an experience, but beneath it, everything continues. Reality is motion wearing a mask. Reality does not stand still in front of you. It performs stillness so well that you mistake the performance for truth. You wake into a world of objects, names, shapes, rooms, roads, bodies, mountains, stars, and memories. And your mind quietly places borders around them. This is a cup. This is a hand. This is a house. This is the sky. This is me. The act feels natural, even necessary, because without these borders, the world would become too fluid to live inside. But underneath every label is a process. The cup is not just a cup. It is matter held in a temporary structure, shaped by heat, pressure, chemistry, and human intention. The hand is not just a hand. It is circulation, nerves, tendons, skin, repair, sensation, warmth, and countless exchanges with the world. The house is not just a house. It is wood or concrete aging, expanding, absorbing moisture, releasing heat, carrying sounds, resisting gravity, and slowly changing under weather and use. Even the self you call me is not a fixed object locked behind your eyes, but a pattern maintained through memory, metabolism, perception, habit, language, and attention. This is the mask reality wears. It presents itself as things, while deeper down, it behaves as events. It gives you nouns, but it lives as verbs. A river is easy to understand this way because its motion is obvious. You know that the river today is not exactly the same water as yesterday, yet you still call it by one name. The name survives because the pattern survives, but the same is true of almost everything, only less visibly. A flame has a shape, but the shape is not a solid object. It is a continuous process of fuel, oxygen, heat, and light. A whirlpool looks like a thing in the water, but it is really a pattern made by moving water. Remove the motion, and the whirlpool does not remain as a hidden object waiting to restart. It is the motion. This is one of the deepest ways to understand the physical world. Many of the things that feel permanent are patterns that persist because motion keeps renewing them. Your body is like this. It is not a sealed possession that merely carries you through time. It is a living pattern rebuilt through intake, use, repair, waste, and regulation. Food becomes tissue, tissue breaks down, molecules are replaced, signals are sent, fluids move, cells divide or die, and still you experience continuity. The continuity is real, but it is not the continuity of a stone statue. It is the continuity of a song. A song can remain recognizable even though each vibration disappears as soon as it is made. Its identity is not in one frozen piece of sound, but in the ordered sequence, the relation, the rhythm. In the same way, you are not made of permanent material in a simple sense. You are made of organized change. And this does not make you less real. It makes reality more subtle than the mind first assumes. Stability in nature often means change that has found a rhythm. A lake can look calm because inflows and outflows balance. A body can maintain temperature because heat is produced, moved, and released in regulated ways. A population can seem steady because births and deaths, arrivals and departures, roughly counter one another. A chemical system can reach equilibrium, not because all molecular activity stops, but because opposing processes occur at matching rates. This is a key truth. Equilibrium is not always stillness. Sometimes equilibrium is motion cancelling into appearance. The mask of rest is created when changes are balanced enough that the large pattern remains. This is why a living cell can be stable and intensely active at the same time. Why a planet can keep its form while everything on and within it changes. Why a star can shine steadily while violent physical processes continue inside it. Why a society can feel familiar while every generation replaces the one before. You see the pattern and call it a thing. Science looks closer and finds circulation, exchange, feedback, pressure, energy, tension, and transformation. This does not mean objects are illusions in the shallow sense, as if nothing exists. A chair really supports you, a wall really blocks you. A body really suffers and heals. The mask is not fake, it is functional. The surface level object is the version of reality your scale can use, but it is not the whole. The chair supports you because forces, materials, bonds, and structure cooperate. The wall blocks you because matter resists compression and overlap. The body heals because biochemical systems recognize damage and respond. The object is the visible summary of invisible activity. And once you understand that, the world becomes less like a warehouse and more like a theater of maintained forms. Everything is being held together by relationships. Remove the relationships, and the object loses its meaning. A book is paper, ink, language, binding, memory, and reader. Without the arrangement, it is only material. A brain is not consciousness because of mass alone, but because of organized activity across cells and networks. A city is not buildings alone, but movement. People, power, water, traffic, waste, money, signals, routines, repairs, decisions, and time. Motion is not something added to reality after things exist. Motion is part of how things exist at all. Even the idea of rest depends on perspective. A parked car rests relative to the road, yet it is carried by Earth, by the sun's path, by the galaxy's motion, by cosmic expansion on scales far beyond local binding. Rest is not absolute in everyday physics. It is chosen relative to a frame. You say the car is still because it is still compared with the street. You say the street is still because it is still compared with your body. You say your body is still because you ignore the hidden motions that sustain it. Stillness is a local agreement, not a final property of the universe. That is why the phrase motion wearing a mask matters. The mask is the frame, the scale, the limit of perception, the language that freezes processes into objects so the mind can survive. But when you lift the mask, you do not find emptiness. You find deep emotion. You find that what seemed solid is structured activity. What seemed quiet is regulated change. What seemed permanent is persistence through renewal. This is not only a scientific idea, it changes the way you feel time. If reality is motion wearing a mask, then loss and continuity are not opposites in the way they first appear. A forest remains a forest while leaves fall. Seeds sprout, fungi digest, insects move, roots communicate chemically, and trees rise and die. A person remains a person while cells change, beliefs shift, memories rewrite themselves, and the body passes through childhood, adulthood, age, and disappearance. The sadness of change is real, but so is the beauty that anything coherent appears at all. The universe does not promise fixedness. It offers patterns that last for a while, patterns strong enough to be loved, studied, named, and remembered. That may be more fragile than permanence, but it is also more alive. A world made of perfect still objects would be a world without growth, weather, thought, digestion, music, fire, evolution, learning, healing, or stars. Motion is not the enemy of order. Motion is the condition that lets order arise, dissolve, and arise again. Too much disorder and patterns fall apart. Too much rigidity and nothing adapts. Life exists in the narrow and miraculous middle, where movement is organized enough to persist and flexible enough to change. And perhaps this is why the still world can feel so comforting and so deceptive at once. You need the mask. You need cups, rooms, names, faces, homes, and selves. You need the world to hold still long enough for you to live inside it. But wisdom begins when you remember that the mask is not the final face. Behind every apparent thing is a history of forces. Behind every stable form is maintenance. Behind every quiet moment is motion arranged so delicately that it becomes peace. So look again at the room around you. Nothing has to visibly tremble for the truth to be there. The air is exchanging warmth. Materials are aging. Light is scattering. Your body is regulating itself. Thoughts are forming and fading. The planet is carrying you. Time is touching every surface. Reality is not frozen. It is continuously becoming. And still, it gives you enough shape to rest your eyes upon. That may be the deepest wonder of all. The universe is motion, but it has learned how to wear masks, convincing enough to be called mountains, oceans, bodies, memories, and home.